Gaze into the deep, star-dusted spiral arms of the Whirlpool Galaxy, a celestial masterpiece spinning silently more than 23 million light-years from Earth. It's one of the most beautiful and recognizable galaxies in our night sky, an elegant pinwheel of light and shadow that has captivated astronomers and dreamers for centuries. But what if I told you that beneath that breathtaking beauty lies a trove of cosmic secrets, strange, baffling, and utterly unexpected phenomena that challenge everything we think we know about how galaxies behave? Today, we're diving deep into the heart of M51 to uncover not one or two, but 30 of the most bizarre mysteries ever observed in our galactic neighbor. From inexplicable radio signals to ghostly structures with no clear origin, the Whirlpool Galaxy is far more than just a pretty face. It's a cosmic puzzle begging to be solved. Imagine for a moment looking up at the night sky and realizing that some of the most profound questions in the universe are hiding in plain sight, wrapped in swirls of starlight and clouds of interstellar dust. Every strange flicker, every anomalous reading, every unexplained structure tells a story, one that scientists are still piecing together. And it's not just about satisfying our curiosity. Unraveling these galactic riddles brings us closer to understanding the fundamental forces that shape not only distant galaxies but our own place in the cosmos. This is a journey into the unknown, a voyage through space and mystery that promises to leave you in awe of just how much we have yet to discover. So settle in and open your mind to the wonders waiting within the Whirlpool Galaxy. Whether you're a seasoned space enthusiast or someone who simply loves a good mystery, what we're about to explore will challenge your imagination and deepen your appreciation for the vast, mysterious universe we call home. From celestial collisions that shouldn't be possible to energetic outbursts with no clear source, each of these 30 phenomena is a chapter in a story still being written, a story we're only beginning to understand. Our journey into the strange and wonderful begins right at the very heart of the Whirlpool Galaxy, with a discovery so energetically bizarre that it forced astronomers to question their understanding of cosmic power sources. Nestled within the galaxy's brilliant core is an object that shines not with visible light, but with an incredible torrent of X-rays. This isn't just a little blip on the detector. It's what scientists call an ultra-luminous X-ray source, and its output is staggering. It radiates more X-ray energy in a single second than our sun emits across all wavelengths in an entire year. That level of energy is simply off the charts, completely defying the limits of what we believe is possible from a normal cosmic event, like a star collapsing or even a typical black hole feeding on nearby gas. When something in the universe produces that much power, the usual suspect is a stellar mass black hole, the remnant of a massive star. But there's a fundamental problem with that explanation. Even the most voracious stellar black hole has a theoretical limit to how brightly it can shine, a boundary defined by its own immense gravity. As matter falls in, it heats up and radiates light, but that very radiation creates an outward pressure that can eventually blow away the incoming stream of material, effectively putting a cap on its own brightness. This mysterious object blows right past that limit, shining hundreds of times brighter than it ever should. It's like discovering a single candle that somehow outshines a stadium's worth of floodlights. So what could possibly be generating such an incomprehensible amount of energy if it's not a standard black hole? One of the leading theories points to a long-sought but never conclusively proven celestial object, an intermediate mass black hole. Think of it as a cosmic missing link. We have ample evidence for small black holes, the ones formed from dead stars, and we've confirmed the existence of supermassive behemoths that anchor the centers of galaxies. But an intermediate mass black hole would sit squarely in the middle, weighing in at perhaps thousands of times the mass of our sun. An object of that size would have a much higher brightness limit, potentially allowing it to account for the furious X-ray output we observe without breaking the laws of physics. Finding one would be a monumental discovery, finally filling a crucial gap in our understanding of how black holes form and grow. Yet, the plot thickens even further because some observations suggest the energy might be beamed, focused into narrow jets like a cosmic lighthouse rather than shining in all directions. This has led to another compelling, if not more exotic, explanation. Perhaps we're not looking at a single object at all, but a new type of stellar system. Imagine a binary pair where a neutron star or a small black hole is orbiting a massive companion star, pulling material from it at an incredibly rapid rate. Under just the right conditions, the geometry of this violent interaction could focus the resulting X-rays into a beam that, by pure chance, is pointed directly at us. From our vantage point, it would appear impossibly bright, a trick of perspective magnifying its true power. And then, of course, there's the most thrilling possibility of all, that we are witnessing something entirely new, a phenomenon driven by physics we haven't yet discovered or don't fully understand. Could it be the signature of exotic particles or a type of energy release we haven't even conceived of? This single point of light, buried in the glow of a distant galactic core, serves as a powerful reminder that the universe still holds profound secrets, challenging us to look deeper and think bigger. It's the perfect place to start our tour of the Whirlpool's wonders, a puzzle that encapsulates the very essence of scientific discovery. While the ultra-luminous X-ray source captivates with its mysterious, concentrated energy, the Whirlpool Galaxy presents another, far more widespread marvel, a stellar nursery operating at a fever pitch. Drifting away from the enigmatic core and out along those majestic spiral arms, we find regions of such intense and prolific star formation that they defy simple explanation. These are not just pockets of new stars, they are veritable factories churning out suns at a rate that leaves astronomers both astonished and deeply curious. For a galaxy of its size and type, the Whirlpool is in the midst of a cosmic baby boom, a period of ferocious stellar birth that is far more typical of galaxies in the much younger, more chaotic early universe. This isn't a subtle statistical anomaly. The evidence is written across the galaxy in brilliant, searing light. Vast clouds of hydrogen gas, the raw material for star formation, glow with an intense pinkish-red hue, illuminated from within by the ultraviolet radiation of massive newborn stars. These are the famous H2 regions, and in the Whirlpool, they are exceptionally large, numerous, and luminous. Telescopes like Hubble reveal intricate structures within these nebulae, dark, snaking filaments of dust, glowing caverns carved out by stellar winds, and thousands of sparkling young stellar clusters, each one a tight-knit family of stars that burst into existence together. The sheer scale of this activity suggests the galaxy is converting its gas into stars with an efficiency and speed that is rarely seen in our galactic neighborhood. So what is stirring the pot, causing this incredible burst of creativity? The primary catalyst appears to be a dramatic, close-range gravitational dance with its smaller companion galaxy, known as NGC 5195. Think of this interaction not as a violent collision, but as an immense and powerful tidal force. As the two galaxies swing past each other in their long orbital embrace, their mutual gravity acts like a colossal hand, violently squeezing and perturbing the vast reservoirs of gas within the Whirlpool's spiral arms. This process does two critical things to the relatively calm gas clouds. First, it compresses them, forcing the gas molecules closer together until they reach the critical density needed to collapse under their own gravity and ignite new stars. Second, it injects a tremendous amount of energy and turbulence into the gas, preventing it from settling into a quiet, stable state, and instead keeping it in a constant, agitated frenzy that is perfectly primed for star birth. This transformative interaction provides a spectacular real-time example of how galaxies evolve and grow through encounters with their neighbors. It's a process that was far more common billions of years ago, making the whirlpool a precious nearby laboratory for studying an era we can otherwise only simulate. But the intrigue doesn't stop with simple compression. The specific patterns of star formation are oddly patchy and intense. Some regions are producing a startling abundance of especially massive, short-lived stars, which will burn brightly and die young in spectacular supernova explosions. These deaths, in turn, seed the surrounding gas with heavy elements and trigger yet more waves of star formation, creating a self-perpetuating cycle of creation and destruction that is reshaping the galaxy's very structure. This exceptional activity forces us to reconsider the life cycle of seemingly stable spiral galaxies. The whirlpool shows us that they are not isolated, serene islands in space, but dynamic systems that can be radically rejuvenated by external influences. The ongoing starburst is essentially setting the clock back on these regions, populating them with a new, young generation of stars that will dominate the galaxy's evolution for eons to come. It's a breathtaking demonstration of the interconnectedness of the cosmos, where a gravitational nudge from a passing neighbor can ignite a firestorm of new suns, lighting up the darkness on a truly galactic scale. But the whirlpool's strangeness isn't confined to the vibrant chaos of its star-forming arms or the brilliant point source in its core. Some of its most profound mysteries extend far beyond what our eyes can see, into the invisible realm of radio waves. Giant, ghostly lobes of radio emission stretch out from the galaxy's main disk, forming a vast, symmetrical structure that dwarfs the entire visible galaxy. These are not mere echoes of the star formation below. They represent a colossal and puzzling output of energy, a phenomenon that current models of galactic evolution struggle to fully explain. It's as if the Whirlpool Galaxy is surrounded by a pair of immense energetic halos, whispering secrets about processes occurring on a scale we are only beginning to comprehend. What makes these radio lobes so anomalous isn't just their size, but their remarkable symmetry and sheer power. They are not chaotic or lopsided, as one might expect from an explosive event like a supernova. Instead, they form a balanced, bubble-like structure that suggests a sustained and focused release of energy from the galactic center. This kind of symmetric outflow is typically associated with active galactic nuclei, where a supermassive black hole is actively feeding and powering gigantic jets that inflate such bubbles into intergalactic space. The puzzle is that the whirlpool's core, while home to that mysterious ultra-luminous X-ray source, is not classified as an active galactic nucleus in the traditional quasar-like sense. It doesn't display the extreme brilliance or the relativistic jets we see in known active galaxies. So what engine is powerful enough and has been running long enough to inflate these immense structures? One compelling theory points back to the collective power of the galaxy's starburst activity. The furious rate of star formation, particularly the birth and rapid death of massive stars, creates a relentless onslaught of supernova explosions and powerful stellar winds. Imagine not just one star exploding, but thousands, one after another, in a continuous chain reaction of cosmic detonations. This could generate a galactic superwind, a vast outflow of hot gas and energetic particles that streams out of the galaxy's plane, potentially inflating these enormous radio lobes as it pushes against the thin medium between galaxies. This would represent a form of galactic feedback on a truly grand scale, where the life cycle of stars themselves regulates the future growth of their host galaxy by blowing away the very gas needed to form new generations. However, the energy required to create and sustain lobes of this size and brightness is immense, and some scientists speculate that stellar activity alone might not be sufficient. This leads to another, more exotic possibility. Could we be seeing the indirect influence of dark matter? While dark matter itself doesn't emit radio waves, its gravitational dominance could be playing a crucial role. The annihilation or decay of certain hypothetical dark matter particles within the galaxy's halo could theoretically release enough energy to generate the observed radio emissions. Alternatively, the precise shape and symmetry of the lobes might be tracing the otherwise invisible gravitational scaffold of dark matter that surrounds the galaxy, providing a unique window into the distribution and properties of this most elusive component of the universe. The true explanation likely lies in a complex interplay of all these factors. The supermassive black hole, though currently quiet, may have had periods of activity in the recent past that helped seed the lobes. The starburst-driven superwind is almost certainly contributing a significant amount of energy, painting the lobes with the signature of 1,000,000 stellar deaths. And overarching it all, the gravitational field of the dark matter halo may be confining and shaping the outflow into the surprisingly orderly structure we observe. These radio lobes stand as a testament to the fact that a galaxy is more than the sum of its visible parts. It is a dynamic system where feedback between stars, black holes, and dark matter governs its evolution over billions of years. Now we arrive at one of the most profound and counterintuitive mysteries at the very heart of the whirlpool itself. For decades, a fundamental rule of galactic astronomy has been the consistent and seemingly unbreakable correlation between a galaxy's central bulge and the monster lurking in its core. The rule is simple: the larger and more massive the central bulge of stars, the more massive its supermassive black hole should be. It's a cosmic scaling law observed across the universe, suggesting a deeply intertwined evolution between the growth of a galaxy and its central gravitational anchor. The Whirlpool Galaxy, with its magnificent and pronounced spiral arms, also possesses a significant central bulge. By all accounts, this bulge should host a supermassive black hole of immense proportions, a behemoth weighing in at tens or even hundreds of millions of times the mass of our Sun. But when astronomers measured it, the numbers didn't just fall a little short, they presented a baffling anomaly. The central black hole appears to be surprisingly, almost inexplicably underweight. This isn't a matter of slight miscalculation or blurry data. The predicted mass based on the bulge's properties and the established scaling relation is significantly higher than the measurements suggest. It's as if you weighed a giant redwood tree, only to discover its root system was no larger than that of a young oak. This discrepancy forces us to confront a series of deeply intriguing questions. Is the black hole genuinely smaller than it ought to be, defying our models of galactic evolution? Or is it simply hidden from our view, its true nature obscured by some cosmic veil? Perhaps most excitingly, could we be looking at a different type of cosmic engine entirely, one that operates by rules we haven't yet written? One compelling line of thought suggests the black hole might not be missing at all, but rather sleeping soundly and hiding its mass exceptionally well. A supermassive black hole is only visible and measurable through its activity, the radiation given off by the superheated accretion disk of matter spiraling into it. If the whirlpool's central black hole is in a period of profound quiescence with very little gas or stars falling into it, it would be virtually invisible. Its mass would have to be inferred by observing the motions of stars very close to it, a difficult task at such a great distance. It's possible we simply haven't been able to get a clear look at the region immediately surrounding the event horizon to take a proper cosmic census. The galaxy's current state, perhaps cleansed of nearby fuel by the intense starbursts in its arms, could have left its central giant starved and silent. Another fascinating theory challenges the very foundation of the problem. Perhaps the scaling law itself isn't as universal as we once believed. The Whirlpool Galaxy is not a solitary island. It's a galaxy deeply shaped by a recent and ongoing interaction. This gravitational dance with its companion may have fundamentally altered its structure. The process of creating such spectacular spiral arms and triggering rampant star formation could have somehow disrupted the standard growth process of the central black hole. Maybe the inflow of gas that would have normally fed the central monster was instead diverted to create new stars across the arms, effectively starving the core and stunting its growth. In this scenario, the black hole isn't missing. It's just on a different evolutionary path, one where external forces interrupted the standard relationship between bulge and black hole. Then there's the most mind-bending possibility of all. What if the object at the center isn't a traditional supermassive black hole in the way we understand it? Could it be something more exotic, like a dense cluster of smaller black holes or other dark objects whose combined gravity mimics a single entity but doesn't follow the same mass rules? Or does its apparently low mass hint at a different formation history altogether, perhaps one where it never went through the intense feeding frenzies that built up black holes in other galaxies? Each of these questions doesn't just seek to solve a single mystery in a single galaxy. It challenges the textbooks, forcing us to reconsider how these cosmic giants are born, grow, and coexist with their galactic hosts. The missing black hole might be the most important clue we have, pointing toward a far more complex and nuanced story of galactic life. Moving from the enigmatic core, our gaze sweeps across the Whirlpool's grand design, and a curious imbalance immediately strikes the eye. This galaxy, so often presented as the textbook example of a perfect spiral, is in fact profoundly lopsided. One of its majestic arms is brilliantly defined, a sweeping arc laden with dazzling star clusters and glowing pink nebulae, while the other appears noticeably fainter, more patchy, and less coherent in its structure. This isn't a trick of perspective, it's a real and puzzling asymmetry, a fundamental broken symmetry in what we expect from a grand design spiral. For an object so iconic, this imbalance is a glaring clue that its beautiful form is not a static portrait but a snapshot of an intense, ongoing gravitational drama. The prime suspect for this cosmic sculpting is once again the galaxy's relentless dance with its companion, NGC 5195. But this interaction does more than just trigger star formation. It literally twists and distorts the galaxy's very skeleton. As the smaller galaxy orbits, its gravitational pull acts like a persistent hand dragging through water, creating a sustained ripple effect within the Whirlpool's disk of stars and gas. The arm that is closer to the companion feels this gravitational tug most powerfully. This constant perturbation does two things. First, it vigorously compresses the gas and dust in that nearest arm, igniting the prolific star formation that makes it appear so brilliantly luminous and well-defined. Second, the gravitational forces actually pull that arm out of its natural, symmetric shape, stretching and amplifying its structure far beyond what the other, quieter arm experiences. This process creates a fascinating real-time demonstration of what astronomers call a density wave. Think of it not as a rigid structure but as a traffic jam moving through a city. The wave itself is the pattern of compression, and as material, stars and gas moves into this jam, it slows down and piles up, sparking star formation. The stars themselves are just moving through the arm. They are not permanently fixed to it. The brighter, more disturbed arm represents the region where the density wave is being most powerfully energized and reinforced by the external gravitational force of its partner. It's the epicenter of the tidal interaction, a perpetual cosmic construction zone where the wave is strongest and most effective at herding material. The other arm, farther from the action, represents a more intrinsic, quieter density wave within the Whirlpool itself, less affected by the interaction and therefore appearing more subdued. The consequences of this asymmetry extend far beyond mere appearance. This lopsided gravitational forcing has a dramatic effect on the galaxy's evolution. The enhanced arm isn't just brighter, it's fundamentally different in its composition and life cycle. The furious pace of star birth there means it is populated by a much younger generation of stars, including many massive blue and short-lived giants. These stars will burn out quickly, dying in supernova explosions that will rapidly enrich that specific region with heavy elements. Meanwhile, the quieter arm follows a more gradual and prolonged timeline of stellar evolution. This creates a galaxy that is, in essence, two different environments evolving on two different clocks, all because of the persistent gravitational nudge from a neighbor. Ultimately, the Whirlpool's asymmetric arms offer a masterclass in galactic evolution. They show us that a galaxy is not a solitary, isolated entity, but a dynamic system constantly reshaped by its interactions. The very features we use to classify galaxies, their shape, symmetry, and structure, are not permanent but are fleeting moments in a long and violent history. The lopsided whirlpool we see today is a transient phase. In a few 100 million years, as the orbital dance continues, the roles may reverse, or the entire magnificent spiral pattern may be rewritten once again, a testament to the universe's endless capacity for change and renewal. Yet, the cosmic anomalies of the Whirlpool Galaxy extend beyond the realm of visible light and radio waves, revealing themselves in the less familiar but equally revealing infrared part of the spectrum. Here, astronomers have uncovered a pervasive and puzzling glow, an excess of infrared radiation that permeates the galaxy, a warmth that cannot be explained by the usual suspects of star formation and interstellar dust. It's as if the entire galactic system is wrapped in an invisible, gentle heat that defies straightforward accounting, pointing to sources of energy or types of material that remain hidden from our view. To understand why this is so strange, we need to consider what normally produces infrared light in a galaxy. The primary source is dust, tiny, microscopic grains of silicon carbon and other heavy elements that are warmed by the light from nearby stars. This warm dust then re-radiates that energy as infrared light. In a galaxy like the Whirlpool, with its furious starburst activity, we expect a lot of this. Young, massive stars flood their surrounding nebulae with intense ultraviolet light, heating the dust clouds to high temperatures and making them shine brightly in the infrared. Astronomers have very reliable models that predict how much infrared emission should come from a given amount of star formation, but in the Whirlpool, the numbers simply don't add up. There is more infrared light, significantly more than these models can account for. It's a widespread, diffuse excess that suggests something fundamental is missing from our equation. So what could be generating this mysterious and pervasive warmth? One compelling line of investigation focuses on the dust itself. Perhaps the composition of the interstellar dust in the Whirlpool is not what we typically assume. Standard models are based on dust found in more placid galaxies like our own Milky Way. But the Whirlpool is a galaxy undergoing a transformative interaction, a place where entire molecular clouds are being shattered and reformed. This violent process could be creating dust grains with very different properties, perhaps larger, fluffier grains or ones made of unusual materials that are far more efficient at absorbing starlight and re-emitting it as infrared radiation. It's possible we are seeing the signature of a dust population that is much better at its job of staying warm, effectively making the entire galaxy glow more brightly in the infrared than our standard textbooks would predict. Another fascinating possibility is that we are missing an entire population of stars, not the brilliant blue massive stars that dominate the light of the spiral arms, but their cooler, quieter, and far more numerous cousins, old red dwarf stars or even brown dwarfs, failed stars that glow faintly with residual heat. These stellar objects are incredibly difficult to detect at the Whirlpool's great distance, as their dim light is easily lost in the glare of their brilliant neighbors. Yet, collectively, they could represent a colossal source of low-temperature warmth. If the galaxy's structure or its recent interaction with its companion has somehow led to an overproduction of these faint, cool objects, their combined infrared output could account for the excess we observe, a gentle, galaxy-wide heat emanating from countless unresolved points of light. And then, of course, we must consider more exotic explanations. Could some of this excess be the signature of processes we haven't yet considered? One intriguing idea involves the potential decay or interactions of hypothetical particles, such as actions, which are a candidate for dark matter. While this remains highly speculative, it's a tantalistic thought that the unexplained warmth could be a faint thermal echo of the universe's most elusive substance. Alternatively, the energy could be originating from the countless faint shocks and turbulence zones within the disturbed gas of the galaxy, areas where energy is being dissipated as heat on a vast scale through mechanisms we don't fully understand or haven't yet modeled. This infrared excess isn't a single glaring anomaly, but a subtle, all-pervasive clue that our understanding of the interstellar medium, the complex ecosystem of gas, dust, and energy that fills the space between stars, is still incomplete, inviting us to look closer and think differently about what gives a galaxy its warmth. As we pull our view back from the warmth of infrared mysteries, we shift our attention to a more fundamental component of the galaxy, its raw building material. The Whirlpool Galaxy, like all spirals, is enveloped in a massive, diffuse halo of neutral hydrogen gas. This primordial hydrogen is the fuel for future stars, and by mapping its radio wave signature, astronomers can trace the galaxy's underlying structure in a way that visible light simply cannot reveal. But when they created this map for M51, what they found was not a smooth, symmetric cloud neatly following the luminous spiral arms. Instead, they discovered a bizarre and chaotic distribution, a pattern of unexpected concentrations and puzzling voids that tells a story of profound disruption and hidden forces at work. The most striking feature is how extensively the hydrogen gas stretches far beyond the bright optical disk we see in photographs. Vast, tenuous clouds of it form an enormous, lopsided envelope around the entire galaxy system. This in itself is a clue to a violent history, as such extended structures are often the telltale fingerprints of a strong gravitational interaction. The gas has been pulled and stretched by tidal forces, much like the wake left behind a boat, with a significant streamer arcing towards and around the smaller companion galaxy, NGC 5195. This directly links the anomalous gas to the galactic dance, showing us that the encounter has not just triggered star formation, but has fundamentally rearranged the galaxy's primary reservoir of future fuel on a colossal scale. Yet, the deeper mystery lies not in the extended gas, but in the distribution within the main disk itself. The hydrogen map does not cleanly overlay the brilliant spiral arms. In some regions, the correlation is strong. Dense knots of gas coincide with the vibrant H2 regions, confirming these are indeed the nurseries where stars are being born. But in other areas, the gas appears to be missing entirely, creating curious voids where the optical starlight shines brightly, but the radio map shows a startling emptiness. Conversely, there are significant concentrations of hydrogen that pool in places with very few young stars, great reservoirs of fuel that for some reason remain untapped and dark. This disconnect between where the gas is and where the stars are forming reveals that the process is far more complex than just gas leading directly to stars. This bizarre arrangement forces astronomers to consider the invisible hand of dark matter. The prevailing theory of galaxy formation holds that a galaxy is not defined by its stars or gas, but by its halo of dark matter. This unseen mass provides the gravitational scaffolding that draws in the ordinary matter, dictating how it moves and collects. The unexpected concentrations and voids in the whirlpool's hydrogen could be a direct reflection of the underlying dark matter distribution. Perhaps the pools of idle hydrogen are sitting deep within the gravitational wells of dense dark matter clumps, held in place and prevented from collapsing into stars by the dynamics of the halo itself. The voids, on the other hand, might indicate regions where the dark matter distribution is shallower or has been disturbed, allowing the gas to be swept away by other forces. But dark matter is not the only sculptor. The galaxy's own stellar population plays a role in this chaotic scene. The furious starburst activity, particularly the countless supernova explosions, acts as a powerful regulatory force. These explosions generate immense shock waves that can heat and disperse huge volumes of gas, effectively blowing bubbles and carving out the very voids we observe in the hydrogen map. This creates a dynamic feedback loop. Stars are born from gas, they live short, violent lives, and then they die in explosions that clear away the surrounding gas, either halting further star formation in that area or triggering it elsewhere by compressing adjacent clouds. The hydrogen distribution is therefore a snapshot of this ongoing battle between gravity's pull and stellar fury's push. Ultimately, the anomalous hydrogen map is a palimpsest, a document written over multiple times, with each layer telling a different part of the galaxy's history. The tidal tales tell of a gravitational encounter that stole and stretched its gas. The voids speak of violent stellar winds and supernova clearing out their neighborhoods. The unexplained concentrations hint at the unseen grip of dark matter. Together, they reveal a galaxy in a state of dynamic and turbulent transition, where the raw material for tomorrow's stars is being constantly reshuffled by a combination of visible and invisible forces, making the Whirlpool's future evolution as unpredictable as it is fascinating. Scattered throughout the Whirlpool's luminous disk are entire cities of stars moving with a purpose that defies the galaxy's serene rotation. These are its globular clusters, ancient and dense spherical collections of hundreds of thousands of stars, each bound together by immense gravity. Ordinarily, these clusters orbit the galactic center in stately, predictable paths, like bees slowly swarming a hive. But in the Whirlpool Galaxy, astronomers have pinpointed a number of these clusters that are anything but ordinary. They are cosmic renegades, streaking through the interstellar void at velocities so high they shouldn't be possible, challenging our understanding of the gravitational forces at play within this stunning spiral. The mystery of these runaway clusters lies in their incredible speed. To achieve such velocity, a cluster must have experienced a phenomenal kick, a gravitational slingshot of immense power. One of the most plausible explanations points to a violent celestial encounter right in the crowded heart of the galaxy. Imagine a dense cluster venturing too close to the galaxy's central supermassive black hole. The extreme gravitational forces there could have acted like a catapult, flinging the cluster away at a tremendous speed in a process known as a gravitational assist. While this is a compelling theory, it presents a logistical problem. The trajectories of many of these high-speed clusters don't neatly trace back to the galactic center, suggesting their origin story might be far more complex. This leads to another captivating possibility. Perhaps these clusters weren't kicked by a single massive object, but were launched by the combined gravitational fury of their own siblings. In the dense inner regions of a galaxy, clusters can interact with each other in intricate gravitational dances. A close passage between two massive clusters could easily transfer enough energy to eject the smaller, lighter one entirely from its orbit, sending it careening out into the galactic disk like a billiard ball struck with perfect force. This dynamic ejection would leave a specific signature, a trajectory that speaks of a multi-body interaction rather than a single, colossal slingshot. Yet, there is an even more dramatic origin story to consider. What if these runaway clusters aren't native to the Whirlpool at all? The galaxy's ongoing interaction with its companion isn't just distorting its shape, it's an act of galactic cannibalism on a monumental scale. As the Whirlpool gravitationally shreds its smaller neighbor, it isn't just pulling in streams of gas, it's also capturing entire star clusters that once belonged to that dwarf galaxy. These captured clusters would enter the Whirlpool with their own unique velocities and orbits, inherited from their original home. They would appear as high-speed interlopers, strange passengers riding the tides of a larger galaxy they were never born in. Their chemical composition could hold the key, as the stars within a captured cluster would have a distinct elemental fingerprint different from the Whirlpool's native clusters. Each of these renegade clusters, therefore, is a fossilized record of a past cataclysm. Their current speed and direction are clues that allow astronomers to rewind the clock, tracing their paths backward through millions of years to pinpoint the moment of their ejection or capture. A cluster flung from the center tells a story of a close brush with a dormant giant. One ejected through a cluster-to-cluster interaction reveals the crowded and violent conditions of the galaxy's inner star cluster population. And a captured cluster is a direct, surviving piece of a dwarf galaxy that was torn apart eons ago, its stars now assimilated into a larger whole. They are not merely astronomical curiosities, they are tracers illuminating the history of gravitational violence that has shaped and continues to shape the beautiful chaos of the Whirlpool Galaxy. Beyond the familiar glow of starlight and the pervasive warmth of infrared, the Whirlpool Galaxy harbors a far more violent and enigmatic secret. Space telescopes designed to see the universe in its most energetic form have detected a persistent, diffuse fog of gamma rays emanating from its spiral structure. These are not the concentrated beams from a pulsar or the brief, brilliant flash of a supernova. This is a widespread, high-energy glow that seems to permeate the galaxy itself. Gamma rays represent the absolute top tier of the electromagnetic spectrum, photons carrying millions of times more energy than those of visible light. Their presence indicates processes of unimaginable violence, and in the Whirlpool, their source remains one of its most compelling and unresolved puzzles. When astronomers go looking for the origin of such powerful emissions, they typically find clear fingerprints. Supernova remnants, the expanding shells of gas from exploded stars, are famous particle accelerators, their shockwaves capable of boosting protons and electrons to near light speed. When these ultra-relativistic particles collide with photons or other bits of matter, they can produce gamma rays. Similarly, rapidly spinning neutron stars known as pulsars often beam out intense radiation across the spectrum, including gamma rays in precise lighthouse-like pulses. Yet, when scientists meticulously catalog every known supernova remnant and pulsar within the Whirlpool, the math falls catastrophically short. The total output from all these individual objects accounts for only a fraction of the diffuse gamma-ray signal that is actually observed. There is a massive excess of energy with no obvious engine, a ghost in the machine that points to something new and extraordinary. This glaring discrepancy has led researchers to consider some of the most exotic possibilities in modern astrophysics. A leading and perhaps most thrilling candidate is the indirect signature of dark matter annihilation. The prevailing theory suggests that dark matter, the invisible substance that makes up most of the galaxy's mass, could be composed of weakly interacting massive particles or WIMP. If two of these hypothetical particles were to collide, the theory states, they could annihilate each other in a flash of energy, producing standard model particles like electrons and positrons, which in turn would generate gamma rays. The Whirlpool Galaxy, with its immense and dense dark matter halo, could be the perfect site for such interactions. The detected gamma-ray glow could be the first faint but detectable signal of this mysterious particle revealing itself not in a lab but on a galactic scale. However, the dark matter explanation, while compelling, is not the only game in town. A more conventional, yet still poorly understood, possibility involves cosmic rays on a truly galactic scale. We know that the Whirlpool's intense starburst activity is generating a tremendous number of supernovae. Instead of looking at each remnant individually, we might be seeing their collective effect. The combined shockwaves from thousands of these explosions could be acting as a giant, galaxy-wide particle accelerator, creating a sea of high-energy cosmic rays that fill the entire interstellar medium. These particles would then constantly interact with the vast clouds of gas and light photons throughout the galaxy, producing gamma rays everywhere at once. This would create a diffuse glow that appears to have no single point of origin, its fingerprint spread uniformly across the spiral arms. There is also a third, more speculative path. Could we be witnessing the signature of a previously unknown class of high-energy objects? Perhaps there exists a population of hyper-efficient cosmic accelerators that we haven't yet learned to identify, something quieter than a pulsar but more enduring than a supernova and far more common. Or maybe the extreme environment of the whirlpool, with its unique gravitational tides and magnetic fields, is enabling known objects to operate in a Chinese letter supercharged mode that our current models don't predict. The gamma-ray mystery ultimately serves as a powerful reminder that our catalog of cosmic phenomena is never complete. The universe is always capable of harboring new physics, new types of objects, and new ways of generating immense energy, waiting in the glow of a distant spiral for us to finally understand what we're seeing. Diving from the high-energy mystery of gamma rays into the intricate tapestry of the whirlpool's visible light, we find a subtler but no less fascinating puzzle woven into the very fabric of its spiral arms. Amidst the brilliant star clusters and glowing nebulae, dark, intricate filaments snake through the galaxy, the cosmic dust lanes that give its spiral structure such striking definition. But these are not simple, passive shadows. When viewed in exquisite detail, they reveal an astonishing level of complexity and fine-scale structure that has left astronomers questioning how such delicate and organized forms could possibly emerge from the chaos of interstellar space. These dust lanes are far more than just empty voids or simple patches of soot. They are dense, cold clouds comprised of tiny solid particles, grains of carbon, and silicate smaller than a fraction of a human hair. In most galaxies, we expect these lanes to follow a relatively predictable pattern, shaped primarily by the overarching gravitational forces of the density wave that defines the spiral arms. Yet in the whirlpool, the dust exhibits a peculiar, almost filamentary quality. It's organized into intricate tendrils, sharp ridges, and swirling patterns that seem too detailed, too finely sculpted to be the product of gravity alone. It's as if an unseen hand has been meticulously combing through the galaxy's dark material, arranging it with a precision that defies simple explanation. So what cosmic forces could be acting as this unseen sculptor? One of the primary suspects is the galaxy's magnetic field. Though invisible to our eyes, a vast, woven web of magnetic field lines permeates the space between the stars. These fields, though incredibly weak by Earth standards, are stretched across light years and can exert a powerful influence on the tiny, charged dust grains. Imagine these minuscule particles as iron filings scattered on a sheet of paper above a magnet. The magnetic field lines can align the grains, guiding them to stack up along specific pathways and creating the long, coherent filaments we observe. In the turbulent environment of the whirlpool, where gas is being violently compressed by the galactic interaction, these magnetic fields could be providing a crucial organizing structure, bringing order to the chaos and sculpting the dust into its strange and beautiful forms. But magnetism isn't the only artist at work here. The intense light from the galaxy's multitude of brilliant, newborn stars exerts its own powerful force. This is radiation pressure, a constant, gentle push exerted by photons of light as they bounce off the dust grains. While this force is minuscule on a human scale, across the vast expanse of a galaxy and over millions of years, it can have a profound effect. It acts like a cosmic wind capable of pushing and sorting dust grains by size. Smaller grains, offering less resistance, can be blown away or swept into specific formations, while larger grains might be left behind, creating a natural sorting mechanism that leads to the intricate patterns and sharp boundaries we see in the dust lanes. This stellar spotlight doesn't just illuminate the stage, it actively rearranges the props. The dynamic interplay between these forces, gravity, magnetism, and radiation, creates a constantly evolving landscape. The gravitational tide from the interaction with the companion galaxy piles the dust up into great waves, while magnetic fields give those waves internal structure and coherence. Simultaneously, the fierce radiation from nearby massive stars erodes and sculpts the surfaces of these dark clouds, evaporating them away in some places and compressing them in others. This creates a breathtaking variety of structures. Some dust lanes appear as sharp, dramatic walls, while others dissolve into delicate, wispy filaments that seem to be on the verge of dissipating entirely. Each pattern is a frozen moment in a slow-motion battle between competing physical forces. This level of detailed organization forces us to reconsider the very nature of the interstellar medium. It is not a placid, homogeneous pool of raw material, but a dynamic, multi-phase ecosystem where different physical processes dominate in different regions. The peculiar dust lanes of the Whirlpool are a testament to that complexity, a cosmic laboratory demonstrating how forces beyond mere gravity can shape the appearance of a galaxy. They remind us that to truly understand the grand design of a spiral galaxy, we must appreciate not only the brilliant stars but also the dark, delicate threads woven between them, each one a clue to the invisible forces that govern the cosmos. As we trace the life cycle of the Whirlpool's stellar inhabitants, a new layer of mystery emerges not from what's present but from what's conspicuously absent. In several key regions across the galaxy, particularly within its grand spiral arms, astronomers have uncovered a demographic puzzle, a glaring deficit of stars of a specific intermediate age. It's as if an entire generation of suns is missing from the cosmic census, creating a strange gap in the stellar population that defies our standard narrative of how star formation unfolds over time. Think of a galaxy's star formation history like the rings of a tree trunk. Each concentric circle tells the story of a specific period of growth, creating a continuous record from the ancient core to the youthful outer edges. In a typical, undisturbed spiral, we expect to see a smooth distribution, a healthy mix of old, middle-aged, and young stars, all coexisting as evidence of a steady, ongoing process of stellar birth. But when scientists analyze the light from certain parts of the Whirlpool, that smooth record is broken. There are plenty of ancient stars that formed billions of years ago, and there is a spectacular abundance of incredibly young stars, blazing blue and hot, born within just the last few million years. The stars that should be in between these extremes, those that would have formed a few 100 million to a billion years ago, are strangely underrepresented. It's a demographic silence, a missing chapter in the galactic storybook. This isn't a minor statistical fluctuation. It's a profound anomaly that points to a dramatic, episodic history of star formation rather than a gentle, continuous one. The most straightforward explanation is that star formation in these regions didn't proceed like a gently flowing river, but more like a sputtering faucet turned completely off for long periods before being violently blasted back on. So what cosmic hand could be responsible for flipping this switch? The prime suspect, once again, is the galaxy's gravitational dance with its companion. The current close encounter is undoubtedly responsible for the recent, furious wave of star birth we see today. But this may not have been the first time the two galaxies have interacted. Their orbital dance likely spans billions of years, meaning they may have had a previous close pass long ago. This earlier encounter could have been the trigger for a powerful but short-lived burst of star formation hundreds of millions of years in the past. That burst would have consumed nearly all the available gas in those regions at that time, creating a populous generation of stars. But then the story turns dark. The most massive and shortest-lived of those stars would have lived fast and died young, exploding as supernova within just a few tens of millions of years. These violent deaths would have done more than just create heavy elements. They would have generated immense shock waves that heated up and expelled the remaining gas from the area. With the raw fuel for new stars suddenly blown away, star formation in that region would have slammed to a halt. it would have entered a long dormant period, a celestial winter where no new stars could form because there was simply nothing left to make them from. This period of quiescence is the gap we see today, the missing intermediate age stars. The recent second close pass with the companion galaxy then reignited the process. Its tidal forces reached into the whirlpool, stirring up fresh reservoirs of gas, funneling new material into those dormant regions and compressing it to once again trigger collapse. This initiated the spectacular starburst we witness now, creating the abundant population of extremely young stars that sits right next to the ancient ones with very little in between. The pattern is a clear signature of a feedback loop where star formation, in its most intense phase, effectively sows the seeds of its own temporary destruction, only to be reawakened by an external galactic event. This cyclical pattern of boom and bust, of violent creation leading to forced dormancy, challenges the simpler idea of galaxies as steady-state systems and reveals them instead as dynamic entities subject to fits and starts, their evolution dictated by both internal cataclysms and external gravitational shocks. While the whirlpool's structure and energy output present profound puzzles, the very elements that make up its stars and gas tell an equally strange and compelling story. When astronomers analyze the chemical composition of M51, they uncover patterns that defy expectations, a cosmic recipe that seems to have been altered by an unseen hand. In most galaxies, there exists a well-established relationship between the abundance of heavy elements, what astronomers call metals, and other galactic properties. Heavier elements are forged in the hearts of stars and scattered by their explosive deaths, so over time, a galaxy should become progressively more enriched. The whirlpool, with its intense history of star formation, should be particularly metal-rich. Yet, the data reveals a more complex and anomalous picture, with certain elements appearing in unexpectedly high or low proportions compared to similar spiral galaxies, creating a chemical fingerprint that is entirely unique. This anomaly isn't uniform, it reveals itself differently across the galaxy's vast expanse. In the bright, star-forming arms, there are pockets where the ratio of elements like oxygen to iron is significantly higher than standard models predict. Oxygen is primarily produced in the short, violent lives and deaths of the most massive stars, those that end their lives as core collapse supernova. Iron, on the other hand, gets a major contribution from a different type of explosion, thermonuclear supernova, which involve the detonation of white dwarf stars and take longer to develop. An excess of oxygen suggests a recent, intense wave of star formation dominated by very massive stars, a starburst so rapid and powerful that it has flooded the local environment with the specific elements those stars produce before the slower iron-producing sources have had a chance to contribute their share. This fits perfectly with the whirlpool's observed frenzy of stellar birth, a localized chemical signature of a recent violent event. However, the plot thickens when we look at the broader galaxy. In some regions, particularly the outer fringes and the extended tidal streams of gas, the overall metallicity is curiously low. This is deeply counterintuitive. A galaxy with such a prolific rate of star formation should have efficiently enriched all of its gas with heavy elements. The presence of these pristine, metal-poor pockets suggests that the whirlpool has somehow managed to accrete fresh, unprocessed gas from its surroundings, diluting the enriched mixture within its disk. But where could this primordial gas be coming from? The most likely source is the ongoing interaction with its companion galaxy, which may be funneling vast reservoirs of virgin hydrogen from the intergalactic medium into the whirlpool's grasp. This would be a form of external contamination, a cosmic infusion of new ingredients that is actively changing the chemical makeup of the galaxy in real time. This leads to another captivating possibility. The chemical anomalies might not be new at all, but rather a lingering ghost of ancient mergers. The whirlpool's current dance with NGC 5195 is a spectacular show, but it may not be the first time it has consumed a smaller neighbor. If it merged with a gas-rich but metal-poor dwarf galaxy in the distant past, the stars and gas from that devoured system would have been assimilated, leaving behind a distinct chemical signature. The stars from that dwarf galaxy would have formed in isolation, from gas that was never enriched by many generations of stars, and their presence within the whirlpool today would create a subpopulation with an unusually low metallicity for their location. We would be seeing the chemical ghost of a galaxy that no longer exists, its stars now forever part of a larger whole. Furthermore, the very process of star formation itself might be operating differently in the whirlpool's extreme environment, leading to unusual nucleosynthesis. The initial mass function, the rule that dictates how many stars of each mass are born in a cloud of gas, might be skewed. Perhaps the intense tidal forces and pressures are favoring the formation of an overabundance of high-mass stars, which would drastically alter the chemical yield, producing more alpha elements like oxygen and magnesium relative to iron. Or the supernova explosions themselves could be different. The magnetic fields or rotation rates of stars in this disturbed galaxy might lead to unusual supernova types that forge elements in different proportions than we see elsewhere. The galaxy could be quite literally crafting elements in a new way, operating a nucleosynthesis factory with a unique set of blueprints. Ultimately, these chemical imbalances are more than just academic curiosities. They are a powerful diagnostic tool. They allow us to read the whirlpool's biography written in the language of elemental abundances. The oxygen-rich regions tell a story of recent, violent starbirth. The metal-poor streams whisper of cosmic cannibalism and the infall of pristine gas, and any peculiar ratios between specific elements hint at fundamental differences in the very way stars live and die in this unique environment. The galaxy's chemical fingerprint is a complex palimpsest written over by successive generations of stars and shaped by both internal processes and external interactions, providing a detailed, if cryptic, record of a life lived in gravitational turmoil. Surrounding the whirlpool's brilliant spiral disk, astronomers have discovered a vast and unexpected glow, an immense halo of ultraviolet light that stretches far beyond the boundaries of the galaxy we see in visible light. This mysterious ultraviolet aura envelops the entire system, a soft, energetic shroud that defies easy explanation. While most galaxies have some form of ultraviolet halo, the sheer scale and brightness of the whirlpools is anomalous, extending to distances that current physical models simply cannot account for with known populations of stars or gas. It's as if the galaxy is wrapped in a cosmic energy field, a silent testament to processes occurring on a scale we are only beginning to appreciate. When we consider what normally produces ultraviolet light in a galaxy, the primary suspects are hot, young, massive stars. These brilliant blue giants flood their surroundings with high-energy UV radiation, and in a starburst galaxy like the whirlpool, we expect a lot of it. But that light should be concentrated in the spiral arms, precisely where these stars are being born. The puzzle is that this ultraviolet halo is diffuse and widespread, existing in regions far from any obvious star-forming activity. It's a pervasive glow that seems divorced from the brilliant hubs of stellar creation below, suggesting its origins are far more complex than simply scattered light from known clusters. This has led researchers to investigate a fascinating possibility. The halo could be the collective light of a vast, hidden population of stars that has evaded our detection. Not the dazzling blue giants, but their smaller, hotter, and more numerous cousins. Specifically, astronomers are looking at stars in late stages of evolution, such as hot white dwarfs or the exposed cores of evolved stars. White dwarfs, the Earth-sized embers left behind after sun-like stars die, can initially be incredibly hot, shining brightly in the ultraviolet for billions of years. If the whirlpool's outer halo contains a far greater number of these ancient stellar remnants than anyone predicted, Their combined faint glow could account for the mysterious ultraviolet excess. It would mean the galaxy's previous generations of stars were far more prolific than we ever knew, leaving behind a ghostly population of dying embers that now outline its true extent. However, stars might not be the only source of this energy. Another compelling theory points to the galaxy's interstellar medium itself. The intense radiation from all the young stars in the core and arms could be ionizing the faint, extended reservoirs of hydrogen gas that surround the galaxy, a process known as fluorescence. Imagine the central regions of the whirlpool acting as a colossal ultraviolet lamp, its light flooding out into the galactic hinterlands and causing the sparse gas there to glow in response. This would require a delicate balance. The gas must be tenuous enough to be transparent to the light, yet dense enough to absorb and re-radiate it efficiently. The ongoing gravitational interaction could have stirred up and dispersed gas to just the right conditions, creating a perfect setup for this large-scale illumination effect. A more dynamic and violent explanation involves the colossal energy output we've already witnessed. The combined fury of countless supernova explosions and powerful stellar winds from the starburst regions doesn't just blow bubbles, it can heat the ambient gas in the halo to extremely high temperatures. Gas heated to tens of thousands of degrees will naturally emit copious amounts of ultraviolet light. This would paint the halo with the thermal signature of the galaxy's own violent feedback, a literal heat signature of the energy being pumped out from the disk below. In this scenario, the ultraviolet halo isn't a static structure but a dynamic, energetic boundary, a testament to the whirlpool's incredible power output and its ability to affect its environment on a truly monumental scale. Yet, the most exotic possibility remains that we are seeing the influence of something entirely different. Could the mechanisms for exciting this gas be more unusual? Some have proposed that the halo might be filled with decaying or annihilating dark matter particles, though this remains highly speculative, or perhaps magnetic fields, which we know can play a role in structuring dust, are also efficient at accelerating particles to high energies in the halo, leading to ultraviolet emission through complex interactions. The true answer likely involves a combination of these factors, a mixture of faint stellar ghosts, fluorescing gas, and thermal emission from heated material. This immense ultraviolet shroud is more than just a pretty glow. It's an integral part of the galaxy's ecosystem, a key to understanding how energy and matter are exchanged between a galaxy and the intergalactic void, and a dramatic reminder that a galaxy's influence extends far beyond the realm of its shining stars. Yet for all the violent drama of its current interaction, some of the whirlpool's most telling clues to its past lie not in its brilliant core or glowing arms, but in the faint, ghostly whispers that surround it. Encircling the main galaxy is a complex web of extremely faint stellar streams and vast arcs of tidal debris, structures so tenuous they are often only detectable through the most advanced image processing techniques. These are the ghost streams, the ethereal remnants of ancient galactic encounters, and they tell a story of a far more violent and cannibalistic history than the galaxy's beautiful symmetry would initially suggest. The very existence of these streams is a clear sign of a process astronomers call hierarchical merging, the fundamental theory that large galaxies like the Whirlpool grow over billions of years by gravitationally shredding and absorbing countless smaller dwarf galaxies. Each stream is a fossilized record of one of these meals, a stellar river that was once the core of a distinct galaxy. As the dwarf galaxy was pulled in by the Whirlpool's immense gravity, it was stretched out, its stars torn away and scattered into long, looping orbits that now form delicate trails around their captor. The fact that we see multiple streams, each with its own unique path and density, indicates that this has not been a single event, but a series of mergers spanning eons. However, the mystery deepens when we try to match these ghosts to their source. The most obvious candidate for creating tidal debris is the Whirlpool's current companion, NGC 5195. Yet, when astronomers meticulously trace the paths of the largest and most prominent streams, their trajectories often don't align with the companion's current orbit or predicted past path. This presents a fascinating puzzle. If these vast structures weren't carved by the galaxy we see today, then what created them? The inescapable conclusion is that the whirlpool has likely consumed other, now completely vanished dwarf galaxies in the distant past, long before its current dance began. These streams are the only surviving evidence of those long-dead galactic neighbors, their stars now forever assimilated into the whirlpool's halo. The timing of these ancient mergers is another layer of the enigma. By studying the density and spread of the stars within a stream, scientists can make estimates of how long ago the disruption occurred. Tighter, more coherent streams suggest a more recent event, as the stars haven't had enough time to disperse along their orbits. Fainter, more diffuse and mixed streams point to a much older catastrophe. Within the whirlpool's halo, we see evidence of both, indicating a history of mergers that occurred at vastly different times. Some streams appear to be relatively fresh, perhaps only a few 100 million years old, while others seem incredibly ancient, dating back to the galaxy's formative years billions of years ago. This paints a picture of a galaxy that has been actively growing through accretion across almost its entire existence. Perhaps the most baffling aspect of these features is their unusual distribution and complex structure. They are not arranged in a neat, symmetrical shell around the galaxy, as some simple models of mergers might predict. Instead, they form a chaotic and lopsided web, with some streams arcing high above the galactic plane and others diving straight through the disk. This complex geometry suggests that the mergers did not happen from a single direction or in a simple, head-on collision. The dwarf galaxies were likely captured from random angles, their incoming trajectories drastically altering the shape and final placement of the debris they left behind. Furthermore, the gravitational influence of the current companion galaxy is undoubtedly stirring this ghostly pot, its ongoing perturbations twisting and distorting these ancient streams, making it even harder to untangle their individual histories. These faint stellar rivers are far more than just celestial scenery. They are a powerful, if cryptic, archaeological record. By mapping their paths and analyzing the chemical composition of their stars, astronomers can perform a form of galactic genealogy. The stars within a single stream will often share a distinct chemical fingerprint, a specific ratio of elements that differs from the stars native to the whirlpool's main disk. This allows scientists to identify which stars belong to which stream and to piece together the properties of the original dwarf galaxy they came from. Was it a small, metal-poor galaxy that formed early in the universe, or a somewhat larger, more evolved system? The answers are written in the light of these ghostly stars, providing a direct window into the building blocks that came together to form the magnificent spiral we see today. Now we turn our attention to a feature of the whirlpool that seems to possess a mind of its own, a rhythmic but unpredictable heartbeat at the very center of the galaxy. The core of M51 is not a steady, constant source of light. Instead, it flickers. Its emissions, particularly in X-rays and other high-energy wavelengths, change in brightness over time, and they do so on timescales that are unexpectedly fast and erratic. This is what astronomers call a variable active galactic nucleus, and its strange behavior is forcing us to reconsider what powers the engine at the heart of this iconic spiral. The variability itself isn't the mystery, it's the speed and pattern of the changes. The brightness of the core can shift significantly over periods as short as days, weeks, or months. In the cosmic scheme of things, where change often unfolds over millions of years, this is blindingly fast. Such rapid fluctuations provide a crucial clue about the size of the emitting region. Because information, even light, cannot travel faster than light speed, a source cannot flicker cohesively across its entire structure faster than the time it takes light to cross it. Think of it like trying to make a massive lake ripple all at once. It's impossible without a coordinated effort across the entire body of water. The fact that the whirlpool's core changes so quickly tells us that the engine driving this activity must be incredibly compact, likely no larger than our own solar system, yet it is capable of outputting the energy of millions of stars. So what could be causing these rapid and unpredictable shifts in brilliance? One of the leading explanations involves the feeding habits of the central supermassive black hole. The light we see comes from the accretion disk, a swirling, superheated whirlpool of gas and dust spiraling into the black hole's event horizon. The rate at which this material falls in is not necessarily constant. It could be gorging itself on a clumpy, irregular diet. Imagine a bonfire. If you throw on a steady stream of kindling, it burns with a consistent flame. But if you toss on large, irregular logs at random intervals, the fire will flare up and die down unpredictably. In the whirlpool's case, the black hole might be consuming dense clouds of gas or even entire stars in fits and starts, causing its energy output to surge and fade in a chaotic pattern that reflects the irregularity of its meals. A second, equally compelling theory points not to the food itself, but to a moving veil obscuring our view. The environment around a supermassive black hole is a chaotic mess of dust and gas. Immense clouds of this material could be drifting through our line of sight, momentarily blocking different parts of the bright accretion disk from our view. As these clouds move, they would act like cosmic thumbprints smudging a lens, causing the overall brightness we perceive to dim and brighten in a complex dance. This wouldn't mean the central engine's output is actually changing. Rather, our view of it is being continually altered. By carefully studying the specific wavelengths of light that dim during these events, astronomers can hunt for the chemical fingerprints of these passing clouds, trying to map the shadowy structures that swirl in the galaxy's inner sanctum. The most intriguing possibility, however, is that we are not looking at a standard active galactic nucleus at all. Traditional active galaxies, like quasars or Seyfert galaxies, have a well-established taxonomy based on their behavior. The whirlpool's core seems to straddle or even defy these categories. Its particular pattern of variability, combined with its other anomalous properties like the apparently underweight black hole, suggests it might represent a rare or transitional state of activity. Perhaps it is a dying quasar, a once ferocious beast now running out of fuel and flickering in its final throes. Or maybe it's a young active nucleus just beginning to awaken, still sputtering to life as it learns to consume the material around it. It could even be an entirely different class of object, one where the accretion disk is warped or unstable in a way that produces these unique and rapid flares. This variable heartbeat makes the whirlpool's core a premier laboratory for studying the most extreme physics in the universe. Each flicker carries encoded information about the intense gravitational fields, magnetic forces, and radiation processes at work just beyond the point of no return. By meticulously monitoring these changes, astronomers are essentially performing remote sensing on a scale previously thought impossible, using light itself to probe the structure and dynamics of a region we will never directly see. The strange variability isn't just a curiosity. It's a direct line of inquiry into the behavior of matter and energy under the most extreme conditions imaginable, offering a fleeting glimpse into the violent, unpredictable nature of the cosmic monster around which an entire galaxy spins. But even after accounting for these violent departures, another explanation emerges from the very nature of the stars themselves. Could the whirlpool's extreme environment be altering the standard pathways of stellar evolution? In a galaxy experiencing such a powerful and sustained starburst, the conditions are anything but normal. Stars are born within clouds that are far denser, more turbulent, and more metal-rich than those in a placid galaxy like our own. These unusual birth conditions might fundamentally change how a star lives its life and how it ends it. perhaps the stars that would normally become the missing types are in the whirlpool, skipping that phase entirely. Their evolution could be accelerated or diverted down a different branch of the stellar family tree, resulting in a different kind of stellar remnant that we haven't yet learned to identify or are not looking for. The rules of stellar physics, while universal, can produce different outcomes when the ingredients are mixed under vastly different pressures. We must also confront the very real possibility that these stars are not missing at all, but are simply hiding in plain sight, their true nature obscured by the very activity that defines this galaxy. The whirlpool is filled with dense dust lanes and glowing nebulae, a visual spectacle that can also act as a cosmic veil. Certain types of evolved stars, particularly those that are cooler and dust-enshrouded, could be incredibly difficult to detect against such a complex and brilliant background. Their faint light in the visible spectrum might be completely absorbed by the intervening dust, only to be re-radiated as heat in the infrared. We could be staring directly at them without realizing it because our telescopes are tuned to the wrong frequency, or because their signature is blended into the overwhelming glow of their younger, brighter neighbors. It's a stark reminder that sometimes the greatest challenge in astronomy isn't finding something new, but simply seeing what's already there in a new way. This demographic mystery, this absence of certain stellar generations, forces us to think more critically about the life cycle of a galaxy as a whole. It suggests that star formation is not a continuous, smooth process, but a stuttering and episodic one, heavily influenced by external triggers and internal feedback. The missing stars are a silent record of a dormant period, a celestial winter that lasted for hundreds of millions of years, only to be shattered by the gravitational shock of a close encounter. They represent a broken link in the chain of stellar generations, a gap in the narrative that tells us as much about the galaxy's violent history as its present-day splendor. By searching for these absent suns, we are not just cataloging anomalies, we are piecing together the biography of a galaxy, one missing chapter at a time. Woven invisibly through the whirlpool star-filled arms and glowing gas clouds is a force both subtle and powerful, its magnetic field. Like the galaxy's nervous system, this vast, unseen web influences nearly everything we see, from the birth of stars to the journey of cosmic rays. While all spiral galaxies possess magnetic fields, the one encompassing the whirlpool is anything but ordinary. Detailed radio telescope observations have mapped its structure, revealing a pattern of startling complexity and baffling strength that presents yet another layer of mystery. The field isn't a smooth, uniform blanket. It shows highly ordered, large-scale patterns in some regions, while in others, it displays chaotic, intense knots of energy, creating a magnetic fingerprint that is entirely unique and deeply puzzling. The most striking anomaly is the field's incredible degree of organization. In the grand design spiral arms, the magnetic field lines are not randomly oriented. Instead, they align with breathtaking precision, closely following the curvature of the arms themselves over vast distances. It's as if a cosmic comb has been drawn through the galaxy, brushing the field lines into near-perfect order. This level of coherence is unusual. Typically, the turbulent chaos of star formation with its supernova explosions and powerful stellar winds should tangle and disrupt magnetic fields, making them messy and disordered. The fact that the whirlpool's field remains so well ordered in the face of such intense violence suggests a powerful and ongoing process is constantly combing it back into place, maintaining its elegant structure against all odds. So what force could be responsible for this immense cosmic grooming? The primary suspect is the galaxy's density wave, the same gravitational pattern that defines its beautiful spiral shape. As the density wave moves through the galactic disk, it doesn't just compress gas to form stars, it also compresses and shears the magnetic field. This process can amplify the field's strength and align its direction, effectively stretching and organizing it along the sprawling spiral arms. In the whirlpool, where the density wave is being powerfully driven by the gravitational interaction with its companion, this organizing effect may be supercharged, creating a magnetic field of unusual clarity and strength. It's a dynamic feedback loop. The wave shapes the field, and the ordered field, in turn, influences how gas flows within the wave, potentially enhancing the very star formation that makes the arms so brilliant. Yet, the story is not one of perfect order. Interspersed with these regions of remarkable alignment are areas of shocking magnetic intensity. These are localized knots where the magnetic field strength is amplified far beyond what standard models predict. They often coincide with the most active star-forming regions, but curiously, they also appear in some seemingly quiescent zones. This presents a classic chicken or egg dilemma. Is the powerful magnetic field in these knots causing the intense star formation by providing extra support to collapsing gas clouds? Or is the furious star formation itself generating and amplifying the magnetic field through the relentless churn of stellar winds and supernova shocks? The answer is likely a bit of both, a self-reinforcing cycle where each phenomenon feeds and strengthens the other in an escalating dance of cosmic energy. The influence of this anomalous magnetic field extends far beyond mere structure. It directly governs the lives of subatomic particles. The whirlpool is a prolific source of cosmic rays, high-energy protons and electrons accelerated to nearly the speed of light. Normally, these particles would travel in nearly straight lines, quickly escaping the galaxy. But the galaxy's powerful and well-ordered magnetic field acts as a colossal labyrinth. The charged cosmic rays become trapped, forced to spiral along the magnetic field lines. This containment effect is why the galaxy boasts such bright and enormous radio lobes. The magnetic fields hold the cosmic rays in place long enough for them to emit the radio waves we detect. The strange configuration of the field doesn't just create pretty patterns. It builds an invisible cage that dictates where the galaxy's most energetic particles can go and how long they stay, fundamentally shaping its energetic output. This leads to the grandest question of all. What is the ultimate origin of this strange magnetic character? Is it generated internally by a unique galactic dynamo process, or is it shaped by external forces? A galactic dynamo is a theoretical process where the rotational energy of the galaxy and the motion of its conductive gas plasma combine to generate and sustain a magnetic field. The whirlpool's unique conditions, its intense, tidally driven turbulence and rapid rotation, might be operating a dynamo that is far more efficient and organized than those found in quieter spiral galaxies. It could be a self-amplifying system, where the motions that create the beautiful spiral arms are the same motions that power a magnetic engine of unparalleled precision. However, we cannot ignore the external sculptor. The whirlpool's ongoing gravitational dance is undoubtedly a prime suspect. The tidal forces from its companion galaxy are not just rearranging stars and gas. They are stirring the entire galactic pot, injecting immense shear and turbulence into the system. This external perturbation could be directly influencing the dynamo, forcing it into a new and more ordered state. It might even be stretching and amplifying pre-existing magnetic fields from the companion galaxy itself, as the two systems exchange not just stars and gas, but also the invisible fabric of their magnetic identities. The anomalous field we see today may be a hybrid, a fusion of the intrinsic magnetic character of two galaxies now becoming one. This intricate, invisible architecture proves that a galaxy is more than just a collection of luminous points. It is a complex system where forces seen and unseen are in constant dynamic conversation, each shaping the other in a billion-year-long embrace. As we sift through the ancient stellar populations of the whirlpool, another demographic anomaly emerges, this time among its most venerable citizens. Globular clusters are typically the grand elders of any galaxy, dense spherical swarms of hundreds of thousands of stars that formed in a single, furious burst during the galaxy's violent infancy. They are cosmic relics, all roughly the same immense age, often over 10 billion years old. In the Whirlpool Galaxy, however, astronomers have made a discovery that upends this settled history. Scattered amongst these ancient clusters are a few brilliant, blue, and unmistakably youthful interlopers. These are globular clusters that appear to be shockingly, impossibly young, their stars burning hot and bright from a birth that occurred not at the dawn of time, but in the relatively recent cosmic past. This discovery is more than just a curiosity. It strikes at the very heart of our understanding of how and when these immense stellar cities are built. The established rule was that the era of globular cluster formation was a brief, explosive period that ended billions of years ago. The presence of these youthful clusters in the whirlpool suggests that rule is not universal, and that under the right conditions, the universe can still forge these massive, bound structures today. Their very existence forces a fundamental question. Are we looking at a miraculous second generation of native cluster formation? Or are these vibrant youngsters actually captured immigrants from a devoured neighbor? The evidence for their youth is written in the color and light of their stars. Ancient globular clusters, having long ago exhausted their supply of massive blue stars, glow with the soft, redder light of their aging stellar populations. These anomalous whirlpool clusters, by contrast, blaze with the intense blue-white light that can only come from massive, hot, and therefore short-lived stars. Their spectra confirm it. They are rich in the specific elemental signatures of recent star birth and lack the atmospheric chemicals that build up over billions of years of stellar evolution. By all standard metrics, these clusters are not ancient relics but stellar toddlers, perhaps only a few 100 million years old. One compelling explanation is that the whirlpool's ongoing gravitational drama has, against all odds, recreated the pristine conditions of the early universe. The violent tidal forces from the interaction with its companion galaxy have generated immense pressure waves, compressing vast clouds of gas to densities not seen since the galaxy's formation. Within these extreme environments, star formation isn't just triggered. It's forced into overdrive, creating not just individual stars but massive, coherent clumps of stars that are born so close together that their mutual gravity instantly binds them into a stable, lasting cluster. This would mean we are witnessing a rare event, the live birth of a globular cluster, a process we thought had ceased long ago, reignited by a galactic collision. Yet there is a competing and equally fascinating possibility. Perhaps these clusters were not born in the whirlpool at all. The galaxy's companion, NGC 5195, is itself a dwarf galaxy being torn apart by the gravitational encounter. Dwarf galaxies are known to host their own populations of star clusters, some of which can be much younger than the classic ancient globulars. As the whirlpool cannibalizes its smaller neighbor, it is not just stealing gas and stars, it is capturing entire stellar systems. These young, bright clusters may have formed within the companion galaxy and are now being assimilated into the whirlpool's halo, their foreign origin betrayed by their unexpected youth. They would be cosmic prisoners of war adopted into a new galactic family. This distinction is crucial as each origin story tells a vastly different tale about galactic evolution. If the clusters are native, it reveals that the whirlpool is a uniquely fertile environment, capable of replicating the universe's most intense early processes through the sheer violence of its current interaction. It demonstrates that a galaxy's evolution is not a linear path but a series of episodes with dormancy followed by violent rebirth. If they are captured, they become trophies of the whirlpool's predatory nature, direct evidence of its growth through the consumption of smaller systems. Their youthful energy would then be a signature not of the whirlpool's own vitality, but of a smaller galaxy's final burst of creativity before its dissolution. The answer may ultimately lie in their motion and chemistry. By meticulously tracing the orbits of these young clusters, astronomers can determine if their paths are consistent with having formed in the whirlpool's disk or if they follow the chaotic trajectories expected of captured objects. Furthermore, a chemical analysis of their starlight can provide a galactic DNA test. The ratio of heavy elements in a captured cluster would reflect the unique chemical history of its original, smaller host galaxy, distinct from the elemental fingerprint of the whirlpool's native stars. These young globular clusters are therefore more than just beautiful anomalies. They are living fossils that hold the key to understanding not only how galaxies build their structures, but how they grow and evolve through both internal creation and external acquisition. But our journey into the whirlpool's invisible architecture doesn't end with mapping its magnetic field's strength and structure. There's an even more subtle and puzzling effect at play, one that requires us to study how light itself twists and turns as it journeys through the galaxy. This brings us to a deeply technical but profoundly mysterious phenomenon known as Faraday rotation. In simple terms, when polarized light waves vibrating in a single plane passes through a magnetized plasma, the magnetic field causes the plane of that polarization to slowly rotate. By measuring this rotation in the radio waves from distant quasars shining through the Whirlpool Galaxy, astronomers can create a detailed map of the magnetic field's strength and direction along our entire line of sight. The results, however, are anything but simple. The Faraday rotation measures across the whirlpool show strange, clumpy, and highly disorganized patterns that stubbornly refuse to align with any of the galaxy's beautiful visible structures, suggesting we are missing a major piece of this magnetic puzzle. What makes this so baffling is the sheer disconnect between what we see and what the magnetic data tells us. You would logically expect the most significant Faraday rotation indicating the strongest magnetic fields to occur in the most prominent features, the dense core, the brilliant spiral arms, and the massive hydrogen cloud. Yet, the map reveals a chaotic patchwork. There are areas of intense Faraday effect where the visible galaxy appears relatively empty and calm, and conversely, there are zones within the busy spiral arms that show surprisingly little polarized rotation. It's as if the galaxy's true magnetic skeleton is invisible to our eyes, operating by its own set of rules and hidden from view within the interstellar medium. This immediately tells us that the simple, direct relationship between starlight, gas, and magnetic strength that we assume in other galaxies is breaking down here in profound and unexpected ways. So what could be causing this bizarre decoupling? One compelling theory points to the complex and turbulent state of the whirlpool's plasma. Faraday rotation doesn't just depend on the strength of the magnetic field. It also depends critically on the density of free electrons that the light encounters along its path. A turbulent, multi-phase interstellar medium, filled with bubbles of hot, ionized gas blown by supernova and shredded by tidal forces, could create a wildly uneven distribution of this electron gas. A path through a faint-looking but electron-rich bubble of hot plasma could produce a strong Faraday signal, while a path through a dense-looking but cooler, neutral cloud might show very little effect. The whirlpool's violent history of interaction and starburst has undoubtedly churned its interior into a froth of different gas phases, making it incredibly difficult to predict how any given line of sight will behave. This leads to an even more intriguing possibility. The magnetic fields themselves might be tangled on unexpectedly small scales. Our telescopes see a smoothed-out version of the galaxy, but the reality might be a labyrinth of magnetic fibers and loops too fine for our current instruments to resolve. In some regions, these microscopic fields might be pointing in all different directions. From a distance, these opposing directions could cancel each other out in their net effect on the passing light, resulting in a measurably weak Faraday rotation, even though the local magnetic energy is actually very high. We could be staring at a region seething with magnetic activity that appears magnetically quiet because its internal chaos is perfectly balanced. It's a cosmic illusion, a cancellation effect that hides the true ferocity of the magnetic environment. Perhaps the most fascinating explanation involves the influence of the magnetic field from the whirlpool's extended halo. Faraday rotation measures everything along the entire path from the distant quasar to our telescopes. This means the signal includes not only the magnetic field within the galactic disk, but also the contribution from the vast, invisible corona of plasma that is believed to surround the galaxy. If this halo possesses its own large-scale, coherent magnetic field, it could be imprinting a Faraday rotation pattern that overlays and obscures the signature from the disk below. The strange, patchy measures we see might not be a map of the spiral arms at all, but a ghostly fingerprint of the halo's magnetic character, a previously unnoticed magnetic sphere of influence that envelops the entire visible galaxy. Ultimately, the anomalous Faraday rotation is a classic example of a mystery that reveals the limitations of our current models. It shows us that a galaxy is not a simple, layered system, but a deeply intertwined mixture of components: thermal plasma, cosmic rays, magnetic fields, and turbulent gas, all interacting in complex ways we are only beginning to understand. The strange patterns are a message telling us that our assumptions about the interstellar medium are too simplistic for a galaxy as dynamic and disturbed as the Whirlpool. Decoding this message will require not just better observations, but new theoretical frameworks that can account for the chaotic, three-dimensional reality of magnetic fields in a universe where nothing is ever as simple as it first appears. Drifting through the vast spaces between the Whirlpool stars, another invisible mystery reveals itself through the subtle shifts in radio wave signatures. Astronomers have mapped clouds of neutral hydrogen gas moving at tremendous speeds, but these aren't simply following the stately rotation of the galactic disk. These are high-velocity clouds, great masses of gas hurtling along on peculiar trajectories that defy the predictable pull of gravity's dance. Their motion is anomalous, too fast, and in the wrong directions to be explained by the galaxy's normal orbital mechanics. It's as if these immense structures have been shot from a cosmic cannon, their paths telling a story of immense forces and violent events that have left their mark on the interstellar medium. When we consider what could possibly accelerate such massive clouds to these incredible speeds, the first and most obvious suspect is the collective fury of star death. The Whirlpool's intense starburst regions are factories for supernova, and each explosion is a cataclysmic event. The expanding shock wave from a single supernova can blast surrounding gas outward at thousands of kilometers per second, carving out vast bubbles in the interstellar medium. In a region experiencing a relentless barrage of these explosions, the effect could be compounded. Shockwave upon shockwave could merge into a single, powerful galactic superwind, a sustained outflow capable of lifting colossal streams of gas right out of the galactic plane and hurling them into the halo. These high-velocity clouds could be the direct result of this stellar feedback, the galactic disk literally coughing up its own raw material under the strain of its immense stellar activity. Yet, not all of the anomalous motions point outward. Some of these high-speed clouds appear to be on inbound trajectories, falling into the galaxy rather than escaping it. This presents a completely different origin story, one of cosmic accretion. The Whirlpool, with its immense gravitational pull, is a magnet for intergalactic material. Vast reservoirs of pristine hydrogen, left over from the formation of the universe, are believed to float in the great voids between galaxies. The galaxy's movement through space, combined with the gravitational tug from its companion, could be funneling this virgin gas into its grasp. These infalling clouds would be messengers from the intergalactic void, delivering fresh, unprocessed fuel that has never been part of a star before. Their high velocity would simply be the terminal velocity of a long, silent fall into the Whirlpool's gravitational well. This interplay between expulsion and accretion creates a dynamic and self-regulating system. The galaxy is both blowing gas out through stellar processes and pulling new gas in through gravity. This cycle is crucial for galactic evolution. The outflows, rich with heavy elements forged in supernova, seed the galactic halo with the building blocks for future generations of stars and planets. The inflows, composed of pure hydrogen and helium, provide a fresh supply of fuel to offset what is lost and to dilute the enriched mix within the disk, potentially explaining some of the chemical anomalies we see elsewhere. The high-velocity clouds are the visible markers of this great galactic breathing, the inhalation and exhalation that governs a galaxy's growth and its chemical future. However, the most intriguing explanation for some of these clouds may lie in the galaxy's tumultuous past. Their peculiar paths and compositions could be the lingering echo of a much older, much more violent encounter than the current dance with its known companion. If the Whirlpool cannibalized another dwarf galaxy billions of years ago, the event wouldn't have been clean. The victim galaxy would have been torn apart, its stars and gas strewn across immense tidal streams. Over eons, the stars in these streams would slowly disperse, but the gas clouds, responding to different hydrodynamic forces, could have collapsed into the distinct, coherent, and fast-moving blobs we see today. These clouds would be the last surviving ghosts of that ancient galactic meal, their motion still carrying the momentum from that long-ago disruption, a permanent record of a cataclysm that otherwise left no visible trace. Determining the true origin of any single cloud requires careful detective work. Astronomers act as cosmic forensic scientists, analyzing two key pieces of evidence: metallicity and trajectory. A cloud's metallicity, its abundance of elements heavier than hydrogen and helium, is a powerful clue. A cloud blasted out by supernova will be heavily enriched, polluted with the ashes of those dead stars. A cloud falling in from the intergalactic void will be virtually metal-free, a pristine sample of the early universe. A cloud that is the remnant of a devoured dwarf galaxy will have a metallicity somewhere in between, reflecting the unique star-forming history of its original home. By combining this chemical fingerprint with precise measurements of the cloud's path through space, scientists can rewind the clock, tracing its journey backward through millions of years to pinpoint the moment of its birth or capture, slowly unraveling the complex history of violence and exchange that is still playing out within the Whirlpool's invisible gaseous realms. Yet another layer of the Whirlpool's mystery reveals itself not in what's blazingly bright, but in what's subtly, pervasively red. As astronomers meticulously catalog the colors and brightness of its countless stars, a curious anomaly emerges in specific regions, a surprising, unexplained excess of red stars. This isn't the gentle reddening of ancient giants, but a pervasive crimson hue that saturates certain areas far beyond what any standard model of stellar populations would predict. It's a demographic oddity, as if an entire unseen class of ruddy suns has been hiding within the spiral arms, their collective glow shifting the color of those regions toward the red in a way that defies conventional astrophysical accounting. The immediate and most logical suspect for this reddening is, of course, cosmic dust. We know the Whirlpool is crisscrossed with intricate, dense dust lanes, and dust is famously efficient at playing tricks with light. It scatters and absorbs blue light more effectively than red, so a star viewed through a sufficient veil of dust will appear redder than it truly is, a phenomenon known as extinction. Perhaps the regions with the red excess are simply those shrouded in particularly thick, localized clouds of dust that our telescopes cannot fully pierce, artificially reddening the light of all the stars behind them and creating the illusion of an overpopulation of red stars. This would be a straightforward case of a cosmic illusion, a trick of perspective and filtration. However, when astronomers attempt to correct for this dust reddening using all the standard tools and models, the anomaly doesn't fully disappear. A stubborn excess of genuinely red light remains. This forces the consideration of a far more exciting possibility: that we are not looking at an illusion, but at a real and previously overlooked population of stars. These could be stars of a type we understand but in a surprising abundance, or they could represent an entirely new, unrecognized stage of stellar evolution. One compelling candidate is a vast congregation of red dwarfs. These are the smallest, coolest, and most numerous stars in the universe, and they burn with a faint, crimson glow for trillions of years. If certain regions of the whirlpool somehow formed a staggering overabundance of these diminutive stars, far more than the standard initial mass function predicts, their combined faint light could create a noticeable red excess that permeates the area. An even more intriguing candidate is the brown dwarf, the failed star. Brown dwarfs occupy the mysterious gap between the most massive planets and the smallest true stars. They are not massive enough to sustain hydrogen fusion in their cores, so after a brief period of glowing dimly from the heat of their formation, they slowly cool and fade, radiating primarily in the infrared and the very red end of the visible spectrum. A dense population of these dark, cold objects, which are incredibly difficult to detect individually at such a great distance, could collectively emit enough subtle, deep red light to account for the anomalous glow. Finding such a large, concentrated population of brown dwarfs would be a discovery in itself, suggesting that the extreme conditions within the whirlpool's turbulent arms somehow favored the creation of these borderline objects over fully fledged stars. This leads to the most speculative and thrilling possibility of all. Could the red excess be the signature of something entirely new? Perhaps we are seeing the light from a hypothetical class of stellar objects that our current models don't predict, stars that evolve differently in the whirlpool's unique environment or that are comprised of unusual materials. Or consider the potential influence of the galaxy's complex magnetic fields. If they are exceptionally strong in these regions, could they be affecting stellar atmospheres in a way that makes them appear systematically redder? The mystery of the red excess is a powerful reminder that our classification of stars is based on a limited sample from a relatively calm galactic neighborhood. The whirlpool, a galaxy in turmoil, might be brewing stellar varieties that challenge our very definitions. Its strange crimson glow a beacon pointing toward undiscovered chapters in the book of stellar evolution. While the Whirlpool Galaxy dazzles with its visible light and perplexes with its invisible magnetic fields, a deeper, more fundamental anomaly is detected by instruments designed to catch the universe's most energetic particles. From the direction of M51, Earth-based observatories detect a constant rain of cosmic rays, subatomic particles, primarily protons and atomic nuclei, accelerated to nearly the speed of light. Every galaxy generates cosmic rays. They are the inevitable byproduct of violent events like supernova explosions. The mystery of the whirlpool is not that it produces them, but that the distribution of their energies, the cosmic ray spectrum, is profoundly strange. It doesn't match the standard profile we see from other similar spiral galaxies or even our own Milky Way. The number of particles at certain energy levels is either far too high or curiously low, creating a jagged, unexpected pattern in the data that points to accelerators and filters within the galaxy that operate by unknown rules. To understand why this is so puzzling, imagine a cosmic ray accelerator with a predictable dial. We think we know how this machine works. The primary engines are the shock waves from supernova explosions. As a blast wave expands into space, it can act like a vast natural particle accelerator, grabbing protons and other atomic nuclei and boosting them to incredible speeds. Based on the whirlpool's incredibly high supernova rate, a consequence of its massive starburst, we would predict an equally immense output of cosmic rays. And we do see a lot of them, but the problem is in the details. The standard model predicts a smooth and steady decline in the number of particles as you look at higher and higher energy levels. It's like expecting a smooth hillside and instead finding a jagged landscape with unexpected peaks and valleys. The Whirlpool's cosmic ray spectrum has these anomalies, bumps and dips at specific energies that should not be there if supernova were the only game in town. This discrepancy forces astronomers to consider the existence of a new class of cosmic ray accelerator hidden within the galaxy's spiral arms. One compelling candidate is a population of hyper-efficient supernova remnants. Perhaps the unique environment of the Whirlpool's starburst regions with their dense gas, powerful magnetic fields, and overlapping shock waves from multiple explosions creates conditions where these natural accelerators can operate at unprecedented efficiency. A supernova shockwave moving through a dense cloud might be able to inject far more energy into particles, boosting them to higher energies than we thought possible, which could account for an unexpected surplus of high-energy cosmic rays. It's the difference between a firecracker going off in an open field versus in a narrow canyon. The confinement and reflection of the blast can dramatically change its effect. Another, more exotic possibility involves the galaxy's central supermassive black hole. Even in its currently quiet state, it may be capable of particle acceleration on a grand scale. Turbulence and intense magnetic fields near the event horizon could fling particles outward, injecting them into the galaxy with energies that imprint a unique signature onto the overall cosmic ray spectrum. This would represent a form of low-level activity that doesn't produce the brilliant light of a full-blown active galactic nucleus, but still manages to contribute a distinct population of high-energy particles to the mix, creating one of those anomalous peaks in the data. However, the strange spectrum might not be about the source of the particles at all, but about their journey. Cosmic rays do not travel in straight lines from their source to our detectors. They are charged particles, and thus they are deflected and twisted by magnetic fields. The Whirlpool's magnetic field, as we've seen, is unusually complex and powerful. It could be acting as both an accelerator and a filter. Certain regions of the galaxy might be particularly effective at trapping cosmic rays of specific energies, allowing them to build up in number and intensity before they eventually escape. Conversely, the magnetic maze might also prevent particles of other energies from propagating freely, effectively filtering them out and creating a deficit in the spectrum. The anomalous data we collect could be a distorted image, a spectrum that has been scrambled by the very magnetic fabric of the galaxy itself during the particle's long journey out into intergalactic space. This leads to the most profound implication of all. The strange cosmic ray spectrum could be our first indirect evidence of physics beyond the standard model. Some theoretical physicists propose that the annihilation or decay of certain types of dark matter particles would produce a very specific signature in the cosmic ray spectrum, a sharp peak at a very precise energy level. If one of the anomalous bumps in the Whirlpool's data were to align with the predicted energy for a specific dark matter particle, it would be a revolutionary discovery. While this remains a highly speculative interpretation, it underscores the ultimate significance of this phenomenon. The anomalous cosmic ray spectrum is more than a celestial curiosity. It is a coded message about the most energetic processes in the universe, and deciphering it could reveal everything from new states of matter to the very identity of the universe's most elusive substance. Given the Whirlpool Galaxy's reputation as a stellar nursery operating at a fever pitch, with its furious star formation and abundant population of massive stars, astronomers expected to see a correspondingly high rate of supernova explosions. These brilliant stellar deaths are the natural, inevitable end for short-lived giant stars, and a galaxy producing them in such numbers should be a constant fireworks display of cosmic detonations. Yet, when they tallied the observed supernova, a specific and puzzling deficit emerged. The galaxy is curiously lacking in a particular class of these explosions, a missing demographic that challenges our understanding of how the most massive stars live and die. The specific shortfall is in a type known as Type II supernova. This isn't just one kind of explosion, but a broad category primarily driven by the core collapse of a single, massive star at least 8 times heavier than our Sun. Given the Whirlpool's well-documented starburst, which churns out these very stars at an exceptional rate, the relative scarcity of their final, fiery farewells is a profound contradiction. It's like walking into a vast factory that's producing an enormous number of matches but rarely seeing any of them actually strike and flare. This anomaly forces us to question whether the factory is working differently than we thought, or if something is quietly snuffing out the flames before we can see them. One compelling theory suggests the problem might start at the very beginning of a star's life. The initial mass function, the cosmic rulebook that dictates how many stars of each size are born from a cloud of gas, might be written differently in the Whirlpool. Perhaps the extreme conditions within its turbulent, tidally compressed arms are skewing star formation. Instead of producing the expected distribution with a healthy number of very massive stars, the process might be favoring the creation of slightly smaller giants. Stars that are still large enough to form supernova, but which may do so in a less luminous or detectable way. Alternatively, it could be producing an overabundance of truly behemoth stars, which brings its own set of strange consequences. This leads to a fascinating and darkly poetic possibility. The missing supernova might be a case of cosmic murder. The most monstrous stars, those born with masses exceeding perhaps 20 times that of our Sun, might not die in a traditional supernova explosion at all. Instead, they could be collapsing directly into black holes without any visible fireworks. In this scenario, the star's entire outer envelope, which would normally be blasted outward in a brilliant display, instead falls inward, swallowed silently by the newborn black hole. The star would simply vanish from the sky, leaving behind only a gravitational signature. If the Whirlpool starburst is indeed producing a higher proportion of these extreme stars, their silent deaths would create a significant deficit in the expected supernova count, a void where spectacular explosions should be. We must also consider the complex social lives of stars, as the majority of massive stars are not born alone but in binary or multiple systems. The gravitational dance with a companion star can drastically alter a star's life cycle. A massive star could have its outer layers of hydrogen stripped away by a greedy neighbor long before it goes supernova. This would fundamentally change the nature of its death. It might explode as a different, less luminous type of supernova that is harder to detect at the Whirlpool's great distance, or the transfer of mass could stabilize the star, prolonging its life and effectively delaying its eventual explosion on a timeline longer than our period of observation. The intense environment of the Whirlpool's crowded clusters might make these binary interactions more frequent and more dramatic, effectively hijacking the standard supernova pathway. Of course, we must also confront the simpler, though no less important, issue of perspective and obscurity. The Whirlpool Galaxy is filled with dense dust lanes, the very same structures that give its spirals such beautiful definition. This dust doesn't just create scenery, it can act as a cosmic veil. A supernova explosion occurring on the far side of a thick dust cloud could have its light significantly dimmed or its specific spectral signatures altered, making it appear fainter or masquerading as a different type of event. Our census of supernova is inherently biased towards those that explode in clear, unobstructed lines of sight. It is entirely possible that a number of these brilliant deaths have simply been hidden from our view, their light absorbed by the dark, dusty curls of the galaxy's spiral arms. This missing supernova problem is more than just a tallying error. It's a crucial puzzle piece in our understanding of galactic feedback. Supernova are primary engines for enriching a galaxy with heavy elements and for regulating future star formation by dispersing gas clouds. If a significant number of massive stars are disappearing without a trace or exploding in unseen ways, our models for how the Whirlpool evolves, how it spreads the elements for planets and life, and how it will eventually use up its gas could be fundamentally flawed. The silence where we expect noise is a powerful reminder that the universe often conceals its most dramatic moments, leaving us to decipher the truth from the echoes and the empty spaces they leave behind. Woven into the tapestry of the Whirlpool's spiral arms, a different kind of anomaly catches the eye, not a missing demographic, but a population of stellar rebels out of place. Scattered far from the vibrant, pink-glowing nurseries where new stars are born, astronomers have pinpointed brilliant blue-white stars and even entire young blue clusters. Their color alone marks them as massive, hot, and incredibly young, stars that burn through their fuel in just tens of millions of years. Their very existence in these quiet galactic suburbs is a profound violation of the rules. A massive blue star is a ticking time bomb. It simply doesn't have the lifespan to slowly drift away from its birthplace. Finding one in isolation is like finding a newborn baby alone in the middle of a desert. It demands an explanation for how it got there and why it's so profoundly out of place. The most dramatic explanation for these solitary blue specks is that they are runaway stars, stellar projectiles shot from their natal clusters by incredible cosmic forces. Imagine a binary star system, two massive stars orbiting each other, diving too close to the supermassive black hole at the galaxy's heart. The immense gravity of the black hole could violently disrupt the pair, capturing one star and flinging the other away at an astonishing speed, sending it careening across the galaxy on a one-way trip into the void. Alternatively, the trigger could be closer to home. In the dense, chaotic environment of a young star cluster, a close gravitational encounter between stars can act like a slingshot, ejecting one of them at hundreds of kilometers per second. These runaway stars would then travel vast distances in their short lives, ending their days far from the crowded stellar cities where they were born, their brilliant blue light a lonely beacon to a violent past. But the mystery deepens considerably when we find not just single stars, but entire clusters of these blue outliers. A compact group of young, massive stars sitting together in the galactic equivalent of a quiet pasture is a far more complex puzzle. A single runaway star is plausible, but a whole cluster of them being ejected together stretches credibility. This has led to a truly captivating theory. Perhaps we are witnessing the results of a previously unknown and utterly extreme mode of star formation. The Whirlpool's gravitational interaction could be generating shock waves of such immense power that they compress isolated, dormant clouds of hydrogen gas scattered throughout the halo, triggering a spasm of star birth in the most unexpected of places. It would be a form of spontaneous stellar generation, creating tiny, isolated islands of youth in a sea of ancient stars. Yet there is another, equally compelling narrative that paints these blue clusters not as native-born rebels, but as captured immigrants. The Whirlpool is not a solitary island. It is a gravitational predator actively consuming its smaller companion galaxy. As it tears NGC 5195 apart, it isn't just stealing diffuse gas and dark matter. It is capturing entire stellar structures that formed within that dwarf galaxy. A young blue cluster that originally belonged to the companion could be stripped away and left orbiting in the outer reaches of the Whirlpool, its origin betrayed by its youth and its incongruous location. Its stars would carry a distinct chemical signature, a different elemental fingerprint from the Whirlpool's native clusters, offering astronomers a way to perform a cosmic ancestry test. The true significance of these blue outliers, therefore, extends far beyond their curious locations. They are tracers of the immense forces that have shaped and continue to shape the galaxy. A runaway star maps the path of a past gravitational encounter with a black hole or a dense cluster. An isolated young cluster could be a signpost marking the passage of a powerful shockwave, or the exact location where a stream of gas from a cannibalized dwarf galaxy finally collapsed. Each one tells a story of violence and motion, a testament to the fact that a galaxy is not a static painting but a dynamic ecosystem where stars can be born in isolation and entire systems can be kidnapped and relocated. They challenge the very idea of a star's place, proving that in the whirlpool of galactic evolution, nothing is ever truly where or what it seems. Beyond the glow of starlight and the chatter of radio waves, the Whirlpool Galaxy whispers yet another secret, this time in the quiet hum of microwaves. Across this specific band of the electromagnetic spectrum, astronomers have mapped a pervasive and enigmatic radiation that blankets the galaxy, a persistent signal that stubbornly resists all conventional explanations. This isn't the well-understood thermal warmth of dust grains or the predictable signature of electrons spiraling in magnetic fields. It is an anomalous microwave emission, a mysterious excess that seems to emanate from the very fabric of the interstellar medium itself, hinting at processes within the galaxy that we have either overlooked or have yet to even imagine. To appreciate just how strange this is, we need to understand what typically creates microwave light in a galaxy. Two primary mechanisms usually account for it. The first is synchrotron radiation, emitted by high-energy electrons as they are forced to spiral along magnetic field lines. The second is thermal emission from interstellar dust, tiny, cold grains that are gently warmed by starlight and re-radiate that energy at longer wavelengths, including microwaves. Scientists have highly refined models that predict how much microwave emission should come from these sources based on observations at other wavelengths. But in the whirlpool, the models fall short. There is a significant diffuse excess of microwaves that these known processes cannot account for, a pervasive glow with no clear point of origin that seems to be woven throughout the spiral arms. This lingering mystery has propelled researchers toward a fascinating and once theoretical culprit, spinning nanodust. The leading hypothesis suggests this anomalous signal could be coming from the smallest dust grains imaginable, tiny molecules of carbon or other materials only a few billionths of a meter across. These nanoparticles are thought to be set spinning at incredible rates, billions of times per second, after colliding with individual atoms or after absorbing a single photon of starlight. This frantic rotation, according to the theory, would cause them to emit radiation precisely in the microwave band. It's a form of electric dipole emission, a completely different mechanism from the thermal glow of larger dust grains. If confirmed, it would mean we are detecting an entire, previously invisible population of the interstellar medium, the smallest and most abundant building blocks of cosmic dust, which have simply been too small and too faint to see by any other means. However, the plot thickens considerably because the unique environment of the whirlpool makes it the perfect laboratory for this phenomenon. The galaxy's intense tidal forces and relentless supernova shocks are likely shattering larger dust grains into these tiny nanoparticles at an exceptional rate, creating a thriving population of them. Furthermore, the powerful radiation from its multitude of young, massive stars could be providing the perfect energy source to set them spinning at the furious speeds required to produce the observed microwave signal. The anomalous emission in this light isn't an error in our models but a direct signature of the whirlpool's violent and prolific nature, a testament to its ability to continually forge and energize the components of its own interstellar material. Yet the spinning dust theory, while compelling, is not the only game in town. The unexplained microwaves could be pointing towards something even more exotic. Some scientists have explored whether we are seeing the faint imprint of magnetic dipole emission. This would involve not just tiny dust grains, but magnetic minerals like magnetite trapped within them. If these magnetic nanoparticles are present and spinning, they could produce a microwave signal with a subtly different signature, one that might better fit the anomalous data. This would imply a far more complex and chemically varied interstellar dust population than we currently comprehend, one rich with specific minerals that have their own unique story to tell about the chemical evolution of the galaxy. And then, of course, we must always consider the most thrilling possibility of all, that the anomaly is a signpost for entirely new physics. Could the microwaves be a product of something not yet in our astrophysical catalogues? While highly speculative, some have pondered whether certain types of exotic particle interactions or even subtle effects related to dark matter could be contributing to this pervasive background hum. The great challenge and the great promise of the anomalous microwave emission is that it is so widespread and so subtle. It doesn't shout from a single point but murmurs from everywhere at once, making it incredibly difficult to pinpoint, but also offering a unique window into the collective behavior of the galaxy's most minuscule components. It is a reminder that even in an age of powerful telescopes, the universe still holds fundamental surprises hidden in plain sight within the gentle whisper of microwaves. Our focus now shifts from the main event to its dynamic partner in this cosmic dance, the smaller and often overlooked companion known as NGC 5195. At first glance, it appears to be a typical dwarf galaxy, a fuzzy, irregular blob of light trailing behind the magnificent Whirlpool. But a deeper look reveals that this companion is anything but ordinary. Its movements and its very structure are caught in a gravitational paradox, exhibiting kinematics that defy the clean predictions of how such galactic encounters should unfold. The standard model for a merger is a graceful, predictable orbital decay, but NGC 5195 is following a far more chaotic and puzzling path. The greatest enigma is its trajectory. Based on its current position and velocity, astronomers have attempted to rewind the celestial clock, tracing its orbit backward through millions of years to understand the history of this interaction. The results are baffling. The path doesn't neatly align with the vast tidal streams of stars and gas that arc around the system. It's as if the companion is moving in a way that is subtly out of sync with the very debris it should have created during previous close passes. This suggests that its orbit is not a simple, closed ellipse gradually decaying under the pull of gravity. Instead, it may be on a much more complex, boxy or highly inclined orbit, a three-dimensional dance that brings it diving through the Whirlpool's plane at a steep angle before looping back out again. This unusual motion could explain why the gravitational disturbance has been so effective at triggering star formation, as it delivers a more powerful and disruptive punch than a gentle, co-planar glide. This strange kinematics immediately raises a profound question about the companion's own history. Is this its first encounter with the Whirlpool, or are we witnessing the latest chapter in a long and violent relationship? The evidence heavily suggests the latter. The companion galaxy shows clear signs of severe and ancient trauma. Its structure is not just irregular, it is profoundly disrupted, with its core oddly offset and its outer regions stretched into long, faint tidal tails that are not perfectly aligned with its current direction of travel. This indicates that NGC 5195 has likely already made at least one, and possibly several, very close passes by the Whirlpool in the distant past. Each passage would have violently stripped away stars and gas, wrenching the smaller galaxy out of its original shape and sending it on a new, altered trajectory. The companion we see today is not a pristine visitor, it is a battered survivor of a billion-year-long gravitational assault. Perhaps the most telling clue to this violent past lies in the companion's own interstellar medium. Unlike the Whirlpool, which is brimming with the gas needed for star formation, NGC 5195 appears to be strangely anemic. A galaxy of its type should still retain a significant reservoir of neutral hydrogen, yet observations show it has been almost completely cleansed of this raw material. The Whirlpool's immense gravity has effectively acted as a cosmic vacuum cleaner, relentlessly sucking the gas away from its smaller companion during their close encounters. This process, known as tidal stripping, has left the companion galaxy starved and quiescent, unable to form new generations of stars. Its remaining stellar population is predominantly old and red, a fossilized testament to a star-forming heyday that was abruptly cut short by its predatory neighbor. Yet, for a galaxy that has been so thoroughly ravaged, it displays a surprising and contradictory spark of life. Deep within its core, astronomers have detected pockets of faint but definite recent star formation. This is utterly counterintuitive. How can a galaxy that has been stripped of its gas suddenly forge new stars? The answer likely involves a phenomenon known as tidal compression. During a very close pass, the whirlpool's gravity doesn't just pull, it also violently squeezes the companion. Any small, dense clouds of gas that manage to somehow survive the initial stripping could be compressed to the point of collapse by this immense pressure, triggering a last, desperate burst of star birth. It's a final stellar gasp, a brief flare of youth ignited by the very same forces that are ultimately leading to the galaxy's dissolution. All of this evidence paints a picture of a system that is far more evolved in its merger process than its current separation might suggest. The strange kinematics of NGC 5195 are not a sign of a new dance, but of one that is entering its final, most complex movements. The companion is not simply orbiting the whirlpool, it is in the advanced stages of being cannibalized by it. Its unusual motion is the wobbling, precessing spin of a galaxy that has lost its structural integrity, its stars already being steadily assimilated into the whirlpool's vast halo. This small, seemingly innocuous blob of light is therefore a crucial key to understanding the whirlpool's own history and future. It is a living demonstration of galactic evolution in its most violent form, a reminder that even the universe's most beautiful structures are built through acts of colossal destruction and assimilation. Yet woven between the whirlpool's brilliant arms and glowing nebulae lies a different kind of mystery altogether, not an excess of light but a profound and puzzling absence. Scattered across the galaxy are strange, dark regions that appear as genuine voids in the cosmos, patches of space that show a startling deficit of emission across nearly every wavelength we can observe. These are not simply the well-defined dust lanes that add dramatic shadow to the spiral structure. These are broader, more diffuse areas where the background radio chatter of hydrogen gas fades to a whisper, the infrared warmth of dust grows cold, and even the visible light from stars seems oddly dimmed. It's as if someone has thrown a cosmic switch, momentarily silencing the usual emissions of the interstellar medium and creating pockets of unsettling quiet within the galactic symphony. What could possibly create such a comprehensive void? The most intuitive explanation points to the galaxy's complex ecosystem of gas and dust. We know that supernova explosions and powerful stellar winds from massive stars can carve out enormous bubbles in the interstellar medium, literally blowing the gas and dust clear out of a region. In a galaxy experiencing a starburst as intense as the whirlpools, this feedback process would be happening on a truly monumental scale. These mysterious dark patches could be the evolved remnants of such events, vast, cleared-out cavities where the raw material for star formation has been violently expelled, leaving behind a volume of space that is simply emptier than its surroundings. The stars within these regions would be older populations whose faint light does little to illuminate the void, creating the impression of a dark gap in the galaxy's fabric. However, the emptiness itself might be an illusion, a trick played by an unseen component. This leads to a more exotic possibility. Perhaps these regions are not empty at all, but are instead filled with a much higher concentration of a very specific and unusual type of cosmic dust. Standard interstellar dust grains are efficient at blocking visible light, but are more transparent to longer wavelengths like radio and infrared. But if the dust in these patches were composed of larger, colder, or more amorphous particles, it could be far more effective at absorbing a wider range of energies. This ultra-efficient dust would act like an incredibly thick, multi-wavelength fog, absorbing the light from background stars and the emission from warm gas, thereby creating a dark patch that appears empty across the spectrum when it is, in fact, filled with an invisible, absorbing material. The most speculative and therefore most thrilling explanation ventures into the realm of the truly unknown. Could the gravitational influence of dark matter be indirectly sculpting these dark regions? We know that dark matter dominates the mass of the galaxy, but it is thought to be distributed in a relatively smooth, massive halo. However, some theories suggest that dark matter might also clump together on smaller scales. If a particularly dense knot of dark matter were to orbit through the Whirlpool's disk, its immense gravity could literally pull the surrounding interstellar gas and dust away, clearing out a region through its gravitational influence rather than through stellar feedback. Alternatively, the presence of such a clump could disrupt the normal processes of cloud collapse, preventing stars from forming in that area and leaving it dark and underpopulated compared to the vibrant regions around it. While this remains a highly theoretical idea, it showcases how these mysterious dark patches could be windows into the invisible scaffolding that underpins the entire visible galaxy. Ultimately, these enigmatic voids serve as a powerful reminder that a galaxy is defined as much by what is absent as by what is present. They are the negative space in a masterpiece of light, and their existence challenges us to look deeper. Whether they are bubbles blown clear by stellar fury, shrouds of ultra-effective dust, or the subtle fingerprints of dark matter's hand, these dark regions are integral to the Whirlpool story. They highlight the dynamic and often violent cycles of matter and energy that continually reshape galaxies, proving that even the quietest, darkest corners of space can hold some of the universe's most compelling secrets. Deep within the Whirlpool's tumultuous star-forming regions, another layer of mystery reveals itself through the peculiar behavior of something we might not expect: water. Not pooled in liquid form, of course, but as individual molecules scattered through space, acting like nature's most precise lasers. Astronomers have detected powerful, concentrated beams of microwave radiation coming from these water molecules, a phenomenon known as maser emission. Think of it as a cosmic lighthouse, but instead of visible light, it emits an intensely focused beam of microwave energy. While water masers are common in the universe, often found in the dusty envelopes around newborn stars, the ones in the Whirlpool Galaxy are behaving in a way that is utterly bizarre. Their emissions are wildly variable, flickering and flaring with an unpredictable rhythm, and their distribution across the galaxy follows a pattern that defies all our models of where and how such activity should occur. The sheer unpredictability of these signals is the first major clue that something unusual is afoot. A typical water maser powered by a young stellar object has a certain rhythm to its variability, often linked to the periodic outbursts of the star itself or the orbital motion of a surrounding disk. The masers in the Whirlpool, however, change in brightness on timescales that are both incredibly fast and completely erratic. They can flare up to incredible intensities in a matter of days or weeks, only to fade away just as quickly without any obvious pattern or trigger. This kind of behavior suggests the environment powering them is highly unstable, subject to sudden and violent changes that our current understanding of star formation cannot easily account for. It's as if the natural amplifier behind these cosmic lasers is being jostled by an unseen hand, its power supply switched on and off at random. This strange variability forces astronomers to consider exotic pumping mechanisms. For a water maser to work, the molecules need to be pumped into an energized state, typically by infrared radiation from warm dust or by collisions in dense, hot gas. The standard models for this process are well established, but in the Whirlpool, these models fail. The intensity of the maser flares is far greater than what the available infrared energy or gas density should be able to produce. One compelling theory is that the unique conditions within the galaxy's tidally compressed arms are generating a new, hyper-efficient pumping method. Perhaps the immense shock waves from countless supernovae are rippling through the molecular clouds, violently compressing the gas and dust to temperatures and densities far beyond the norm, creating temporary and incredibly powerful conditions for maser action that we simply don't see in common galaxies. Furthermore, the distribution of these masers is just as puzzling as their behavior. They are not neatly confined to the most obvious and active stellar nurseries. Instead, they pop up in seemingly random locations, some in the heart of brilliant H2 regions, but others in quieter, more peripheral zones of the spiral arms, and a few even appear far from any significant star-forming activity altogether. This scattered, almost chaotic placement implies that the specific conditions needed to trigger these powerful emissions can occur in a much wider variety of environments than we ever thought possible. It suggests that the recipe for creating a cosmic water laser is not as exclusive as our textbooks claim, and that the Whirlpool Galaxy has somehow discovered alternative ingredients or methods. This bizarre distribution opens the door to even more fascinating possibilities. Could some of these masers be powered by previously unrecognized astrophysical phenomena? Instead of being tied to the birth of stars, might they be signatures of their death? The intense shockwaves from supernova remnants expanding into cold, dense clouds of water-bearing gas could potentially pump masers in a very different way, creating brilliant but short-lived signals that appear far from any nursery. Another, more speculative idea involves the influence of the galaxy's strong and ordered magnetic field. If these fields are exceptionally powerful in certain areas, they could be influencing the collision rates between water molecules and other particles, effectively tuning the efficiency of the maser process and turning it on in places where it would normally remain silent. Ultimately, the anomalous water masers are more than just a curious sideshow. They are highly sensitive probes of the extreme physical conditions within the Whirlpool's interstellar medium. Their unpredictable flickering is a direct response to the temperature, density, and energy flow in their immediate environment. By studying their bizarre behavior, astronomers are essentially reading a diagnostic report on the most violent and chaotic processes at work within the galaxy's gas clouds. They serve as a stark reminder that even a molecule as familiar as water can act in profoundly unfamiliar ways when placed in a cosmic pressure cooker like the Whirlpool, offering a unique and flickering window into the hidden forces shaping this magnificent galaxy. But just as we grapple with the missing endpoints of massive stars, the Whirlpool Galaxy presents us with a completely opposite and equally baffling demographic puzzle, a peculiar surplus of stellar ghosts in its final act. In specific regions, astronomers have catalogued a surprising overabundance of planetary nebulae, those beautiful, glowing shells of gas expelled by dying stars. While these cosmic butterflies are common enough, their numbers in parts of the Whirlpool seem to defy the expected statistics, creating a population boom where one simply shouldn't exist based on the number of potential parent stars. To understand why this is so strange, we need to look at the life cycle of a typical star. A planetary nebula is not formed by just any star. It is the final, parting gift from a low to intermediate mass star, one similar in size to our own Sun. After billions of years of stable life, such a star puffs off its outer layers as it dies, leaving its hot, exposed core to illuminate the expanding shell of gas. The number of planetary nebulae we should see in a galaxy is directly tied to the number of these specific aging stars present. It's a straightforward demographic relationship that has held true in other galaxies. Yet, in the Whirlpool, the math doesn't add up. There are simply too many of these glowing shells for the estimated population of stars that could have produced them, as if the galaxy has been secretly hoarding a hidden generation of Sun-like stars that we can't otherwise see. One compelling line of investigation suggests we might be witnessing the consequences of accelerated stellar evolution. The Whirlpool is a galaxy under extreme duress, its gas and stars churned by immense gravitational tides. This violent environment could be fundamentally altering how stars age. Perhaps the stress of a close encounter with another star, or the intense pressure of moving through a densely packed region, is causing some stars to shed their envelopes prematurely. This would effectively shortcut their evolution, turning them into planetary nebulae faster than they would under normal, placid conditions. In this scenario, we aren't seeing more deaths, but rather deaths that are happening ahead of schedule, creating a temporary spike in the number of these objects that will eventually settle back to normal levels. Another fascinating possibility involves the unique chemistry of the whirlpool. The composition of a star's atmosphere can drastically influence the formation and visibility of its resulting planetary nebula. The galaxy's intense starburst has heavily enriched the interstellar medium with heavy elements. Stars born from this enriched gas might develop thicker, more massive envelopes. When these stars eventually die, they could eject more material, creating larger, brighter nebulae that are simply easier for our telescopes to detect. What we perceive as an overabundance might actually be an effect of enhanced visibility. We're seeing a higher percentage of the total because the nebulae themselves are more spectacular and impossible to miss, while their fainter counterparts in other galaxies go unnoticed. We must also confront a more fundamental astronomical challenge: distance. Accurately measuring the distance to another galaxy is notoriously difficult. All of our estimates for the number of stars in the whirlpool are based on assumptions about its overall distance from us. If our current distance calculation is even slightly off, it would throw off all our stellar population models. If the whirlpool is actually closer to us than we believe, then the stars within it would be intrinsically fainter. This would mean there are actually more stars there than we've calculated to account for the light we see, which could neatly explain the surplus of planetary nebulae. The anomaly wouldn't be in the galaxy's evolution, but in our own cosmic cartography, a simple error in measurement creating a profound mystery. Perhaps the most elegant explanation lies in the whirlpool's history of galactic cannibalism. We know it has likely consumed smaller dwarf galaxies in the past. Those devoured systems would have brought with them their own populations of stars, including a full complement of aging suns ready to become planetary nebulae. The apparent overabundance we see today could be the combined contribution of two distinct stellar populations: the whirlpool's native stars and the assimilated stars from its victims. We would be seeing a demographic echo of those long-dead galaxies, their final generation of stars now dying within a new galactic home, their glowing remnants adding to a census they were never originally part of. Each unexpectedly bright shell could therefore be a fossilized memory of a past merger, a ghost from a galaxy that no longer exists. And now we reach perhaps the most synchronously bizarre mystery of them all, a phenomenon that suggests the entire galaxy is operating on a connected, rhythmic clock. Across the vast expanse of the whirlpool, astronomers have detected a strange and pervasive form of cosmic choreography, coordinated time variability observed simultaneously across multiple, vastly different wavelengths of light. It's not just that one part of the galaxy flickers in X-rays while another flares in radio waves. The truly baffling discovery is that these changes often happen in lockstep. A region might brighten in visible light at the exact same time as a completely different area far across the spiral arms surges in infrared emission, while the core's radio output dips in a seemingly related pattern. This isn't random noise, it's a symphony of light whose conductor remains entirely unknown, suggesting a physical connection between events separated by thousands of light years, a concept that defies our standard understanding of cause and effect. Imagine tossing a single stone into a still pond and watching ripples spread outward. That's a local event. Now, imagine tossing dozens of stones into different parts of a massive lake and seeing every single ripple rise and fall in perfect unison. That's the scale of the mystery we're confronting. The sheer distances involved make direct communication between these events impossible, as even light itself would take centuries to travel from one flickering point to another. Whatever is orchestrating this galactic-scale synchronicity must be a fundamental property of the system itself, an underlying process or structure that can transmit changes across the entire galaxy almost instantaneously, or at least on timescales far faster than light travel would allow. It points to a level of interconnection that we are only beginning to fathom. So what cosmic mechanism could possibly link events across such immense voids? One of the most compelling suspects is the galaxy's magnetic field, which we now know is unusually powerful and well-ordered. Think of this magnetic web not as a passive feature, but as a dynamic, living structure. A sudden release of energy in one location, like a cluster of supernova, could send a powerful shockwave rippling not just through the gas, but along the magnetic field lines themselves. This magnetic shock could travel across the galaxy, compressing gas and triggering secondary bursts of star formation or energizing particles wherever the field is strongest, lighting up different wave bands in a coordinated sequence. The magnetic field would act like a vast, rigid network of wires, conducting energy and information to far-flung regions, making the entire galaxy respond as a single, interconnected unit. Another fascinating theory points to the gravitational influence of the dark matter halo. While dark matter doesn't interact with light, its gravitational pull is the primary force shaping the galaxy's overall structure. If the dark matter distribution contains subtle density waves or resonances of its own, these could rhythmically tug on the ordinary matter, the gas and stars throughout the disk. A periodic compression from this unseen hand could simultaneously trigger activity in multiple, widely separated locations. Star formation rates could increase, gas clouds could collapse, and accretion onto black holes could be enhanced, all in response to this galaxy-wide gravitational pulse. The coordinated variability would then be a shadow, a visible echo of the invisible dark matter skeleton vibrating in a way we are only just learning to detect. We must also consider the possibility of a central conductor. The supermassive black hole, despite its apparent quiescence, might be the source. It could be experiencing faint, rhythmic episodes of accretion that we cannot directly see, but whose effects are broadcast across the galaxy. Energetic particles or jets, even if weak and diffuse, could be shot out along the rotational axis, eventually impacting the gas in the outer disk and halo millions of years later. If the black hole's activity has a regular period, it could be setting the beat for a galactic drum, with different regions responding at different times depending on their distance from the core, creating the illusion of coordinated action when it is actually a delayed but rhythmic cascade. Yet, the most profound implication of this multi-waveband variability is that it forces us to see the whirlpool not as a collection of independent systems, a core, some arms, a halo, but as a single, integrated organism. A change in one organ affects the whole body. The star formation in the arms is linked to the energy output in the core, which is tied to the particle acceleration in the halo. It reveals a galaxy as a complex, self-regulating ecosystem where feedback loops operate on truly gigantic scales. This mysterious synchronicity is the strongest clue yet that to truly understand a galaxy, we must learn to listen to its entire symphony at once, hearing how the notes struck in one instrument resonate through all the others, a harmony of physics we are only beginning to appreciate. From its mysteriously underweight central black hole and its inexplicable ultra-luminous X-ray source to the anomalous gamma-ray fog and the coordinated, galaxy-wide flickering across multiple wavelengths, the Whirlpool Galaxy has proven itself to be a cosmos of contradictions. We've journeyed through 30 of its deepest puzzles, each one a testament to the fact that our universe delights in defying expectation. This isn't just a beautiful spiral, it's a dynamic, turbulent, and deeply interconnected system where the furious starbirth in its arms is linked to the quiet enigma of its core, where the invisible hand of dark matter sculpts the visible gas, and where the past history of galactic cannibalism is written in the faint streams of stars and the chemical fingerprints of its suns. These phenomena collectively show us that a galaxy is not a static island, but a living, breathing entity. It's a system where feedback loops between stars, gas, black holes, and dark matter dictate its evolution in ways we are only beginning to map. The Whirlpool's mysteries are from its runaway star clusters and its missing supernova to its anomalous magnetic fields and its inexplicable water mazes are not mere curiosities. They are the questions that will drive the next generation of telescopes and theories, pushing us to rewrite our textbooks on galaxy formation, stellar evolution, and high-energy physics. So the next time you see an image of this celestial whirlpool, remember that you're not just looking at a pretty picture. You're looking at a dynamic and chaotic ecosystem, a cosmic laboratory where the fundamental laws of physics are being tested and expressed in their most extreme forms. It stands as a powerful reminder of how much we have yet to discover and how the universe always has another layer of wonder to reveal. Now we want to hear from you. Which of these 30 strange phenomena captured your imagination the most? Was it the silent, disappearing stars that collapsed directly into black holes, or the eerie, synchronized flickering that suggests the entire galaxy is connected by an unseen force? Let us know in the comments below. We love discussing these cosmic mysteries with you. And if you enjoyed this deep dive into the unknown, make sure to subscribe and hit the bell so you don't miss our next journey into the deepest wonders of the cosmos. The universe is full of mysteries, and we're